Imagine a world with no light, no shadow, no change. A perfect, featureless ocean of pure potential, where every single point is identical to every other. This was the universe in its infancy, a state of flawless symmetry. But perfection, it turns out, is fragile. The story of our existence is the story of how that perfection was shattered, and how in its breaking, it created everything we see, and everything we are. This is the story of the final day of perfect symmetry. A day that lasted less than a single instant but contained the blueprint for all of cosmic history. Welcome to the Science for Deep Sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. The character of perfection. Before the beginning, there was a state that our brains just aren't built to handle. Scientists and thinkers, from Einstein to Hawking, have wrestled with how to describe this primordial condition. The most common idea is a singularity, an infinitely small point of infinite density and temperature. At this point, our known laws of physics completely break down. It's a boundary not of space, but of our understanding. Time and space, as we know them, didn't exist yet. Asking what came before the Big Bang is like asking what's north of the North Pole. The question itself doesn't make sense. In this state, whatever it was, the universe had a terrifying and profound kind of perfection, absolute symmetry. In physics, a system is symmetrical if you can do something to it, and it still looks the same. Think of a perfect sphere. Rotate it any way you like, it's still the same sphere. Now, imagine that idea applied to the entire universe. In its first moments, the universe was so uniform that every point in space was indistinguishable from any other. Every direction was the same. The laws of physics themselves were unified and symmetrical. This wasn't just spatial symmetry. The very forces that run our reality today, electromagnetism, the weak nuclear force, the strong nuclear force, were all merged into a single, unified, super force. The idea, known as a grand unified theory, or GUT, suggests that at the unimaginable energies of the early universe, the differences between these forces just vanished. They were all interchangeable parts of one elegant whole. This universe was a realm of pure potential. It was like a flawless, still pond, no ripples, no waves, no distinctions. Every drop of water identical to its neighbor. It was a state of maximum order, but also profound emptiness. In this perfect symmetry, there could be no structure. No galaxies, no stars, no planets, no people. Structure, by its very nature, needs a break in the pattern. It needs an imperfection, a lumpy part, a dense part, a place that is different from another place. This perfect universe had no features, no information, no story to tell. It existed in a state where time itself had no forward arrow, because without change, time is a meaningless concept. Some physicists, like Stephen Hawking and James Hartle, proposed a no-boundary proposal to get around the thorny problem of the singularity. They suggested that if we could trace time backwards, the very idea of time would get fuzzy and blend into space. In this picture, the universe didn't have a sharp starting point. It just was a smooth, self-contained geometry with no problematic beginning. But even in this elegant model, the core idea holds. The initial state was one of profound symmetry. A universe balanced on the finest of points, a quiet, featureless eternity. It was the very definition of order. But as we're about to see, cosmic order is inherently unstable. Perfection, it turns out, can't last. This placid state was poised on the brink of the most violent and creative event in the history of everything. It was living out its final moments. The philosophy of a flawless universe. To really get our heads around this, we have to step beyond physics for a moment and touch on philosophy. What does it even mean for something to be perfect? In our world, Perfection is an ideal we chase but never catch. It implies a state with no flaws, no inconsistencies, and no room for improvement. But this concept is full of weird paradoxes. A perfect being, for example, would have no reason to act or change, because action itself is an attempt to fix an imperfection. Existence as we know it is all about happening, about doing, about becoming, all of which imply that things aren't perfect to begin with. Now, let's apply that to the early universe. A perfectly symmetrical cosmos is, philosophically, a cosmos without any content. If every point is the same, no point carries any unique information. If every moment is the same, there's no story, no history. It's like a book with infinite pages, but every page is blank. Is that book perfect, or is it perfectly useless? The ancient Greek philosopher Plato argued that our world is just a shadow of a true, perfect reality made of unchanging forms. He believed that true knowledge came from pure reason, accessing a God's eye view of these perfect blueprints. In a way, the early universe was the ultimate physical version of this Platonic ideal. It was pure mathematical elegance, governed by a single, unified law. It was reality stripped of all the messy, complicated, and random details that define our existence. It was the asterisk idea of a universe, before it became a universe. But here's the cosmic irony. This state of ultimate perfection is also a state of ultimate sterility. In this flawless balance, nothing can happen. Life, consciousness, and creativity all spring from complexity and the interplay of different parts. They require things to be different. They need lumps and voids, hot spots and cold spots, matter and energy clumped into stars and spread into nebulae. All of these things are violations of perfect symmetry. So, the perfect universe is a dead universe. It's a cosmic thought experiment that could not, and did not, last. Its very perfection was its own undoing. It was a state known as a false vacuum, a state that seems stable but is actually incredibly precarious. Imagine a ball resting in a small dip at the very top of a huge hill. It's stable for now, but the tiniest nudge will send it rolling down to a much lower, more stable energy state at the bottom. The state of perfect symmetry was that ball at the top of the hill. The laws of physics, while symmetrical, held the potential for a more stable energy state, one where the symmetry was broken. This transition wasn't a question of if, but when. The final day of perfect symmetry was just the infinitesimal moment before the inevitable fall. The universe was like a pencil balanced perfectly on its point. The setup is flawlessly symmetrical, but it's also profoundly unstable. Any tiny disturbance would be enough to make it topple, picking a random direction to fall in, and shattering that symmetry forever. This collapse wasn't a flaw in the perfection, it was a consequence of it. Perfection, in a dynamic reality, is the most unstable state of all. The seeds of chaos. So what gave the perfectly balanced universe that nudge? The culprit is the weirdest and most fundamental aspect of reality we know: quantum mechanics. At the quantum level, the universe is not a quiet, static place. Even in a perfect vacuum, there's a constant fizz and crackle of energy. These are quantum fluctuations, tiny, spontaneous variations in energy that pop in and out of existence. They are a fundamental property of quantum fields. Even at its lowest energy state, a field is always jittering. In our huge universe today, these fluctuations are microscopic. But in that primordial, hyper-dense point of pure potential, these fluctuations were everything. They were the one source of randomness in an otherwise perfect system. The false vacuum, the state of perfect symmetry, was simmering with these quantum jitters. They were the microscopic tremors running through the pencil balanced on its tip. While the asterisk laws of physics were symmetrical, the actual state of the vacuum wasn't immune to this randomness. At some point, one of these fluctuations would have been just enough to tip the scales. It would have nudged the universal state, represented by a hypothetical energy field called the inflaton field, off its precarious perch. Once that happened, the fall was instantaneous and catastrophic. Physicists call this spontaneous symmetry breaking. It's spontaneous because no external force caused it. It's just an inherent property of the system itself. A classic analogy is a cooling magnet. At high temperatures, the tiny magnetic domains inside a piece of iron point in random directions, canceling each other out. The iron isn't magnetic. This is a symmetrical state. No direction is special. But as the iron cools, the domains suddenly snap into alignment, all pointing the same way, creating a north and south pole. The system has spontaneously chosen a direction, breaking the symmetry. The laws of physics don't care which way the magnet points. They're still symmetrical. But the magnet itself is now asymmetrical. The early universe went through a similar, but far more profound, phase transition. As the universe began, it was in this high-energy, symmetrical state. But this state was unstable. A quantum fluctuation provided the trigger, and the universe began to cool, dropping to a lower energy state. In doing so, the unified superforce couldn't stay unified anymore. Just like steam condensing into liquid water, the fundamental forces began to condense, or freeze out, from the primordial unity. This wasn't a gentle process. The transition from the false to the true vacuum released a colossal amount of energy. This energy acted like an anti-gravity force, driving space itself to expand at a mind-boggling, exponential rate. This is the period we call cosmic inflation. First proposed by physicists like Alan Guth and Andre Linde, inflation theory suggests that in the first tiny fraction of a second, from around 10 cubed to the power of 6 to 10 cubed squared seconds after the beginning, the universe underwent an astonishing growth spurt, expanding by a factor of at least 10 to the power of 26. A region of space far smaller than a proton ballooned to the size of a marble in less than an instant. This explosive expansion was the true shattering of perfection. It took the perfectly uniform state and stretched it to unimaginable proportions. And crucially, it also stretched those tiny quantum fluctuations. The microscopic, fleeting jitters of the quantum world were magnified to cosmic scales. These stretched-out fluctuations became the seeds of all future structure. They were the tiny differences in density from one place to another that gravity would later grab onto. The final day of perfect symmetry was over. The bang had begun, a cascade of broken symmetries. The breaking of that first, perfect symmetry wasn't a single event. It was the first in a cascade of shattering moments that defined the character of our new reality. The universe's journey from a simple, unified state to a complex, differentiated one happened as a series of symmetry-breaking events, each one changing the cosmos forever. The very earliest break happened at the end of the Planck epoch, about 10 to the power of 4 cubed seconds in, when gravity split off from the other forces. After that, during the grand unified theory, GUT, epoch, the strong, weak, and electromagnetic forces were still a single, electronuclear, force. This lasted until the universe was about 10 cubed to the power of 6 seconds old. At this point, the universe had cooled enough for the next major symmetry to break. The strong nuclear force, the cosmic glue that holds atomic nuclei together, split off from the electroweak force. This was another phase transition. The universe chose a new, lower energy state, and another layer of its initial perfection was peeled away. The strong force became its own thing, with its own rules and its own carrier particle, the gluon. The electromagnetic and weak forces, though, remained tangled together for a little while longer. The universe kept expanding and cooling. At around 10 squared seconds after the Big Bang, the temperature dropped to a point where the final unification couldn't hold. This was the moment of electroweak symmetry breaking, an event explained by the standard model of particle physics and the famous Higgs mechanism. To get this, we have to introduce another key player, the Higgs field. In the very hot, early universe, the Higgs field was off, its value at 0. In this state, all particles were massless, zipping around at the speed of light. There was no difference between the photon, electromagnetism's carrier, and the W and Z bosons, the weak force carriers. They were all one family. But as the universe cooled, the Higgs field, like our cooling magnet, spontaneously broke its symmetry. It switched on, settling into a non-zero value everywhere in space. This changed everything. As the Higgs field turned on, particles moving through it started to interact with it. Some, like the photon, didn't interact at all and stayed massless. But others, like the W and Z bosons, dragged against the field, and in doing so, they acquired mass. This interaction is what makes them heavy and short-ranged, which is why the weak force only operates over tiny, subatomic distances. At the same time, other fundamental particles like electrons and quarks also got their mass from this interaction. This was the final schism. From one perfect, unified force, we now had 4 distinct forces: gravity, strong nuclear, weak nuclear, and electromagnetism. Each with its own strength, range, and carriers. The universe had become fundamentally more complex. The very property of mass, which is so crucial to our existence, is a result of a broken symmetry. Without it, there would be no atoms, since electrons wouldn't be bound to nuclei. There would be no complex structures at all. This cascade of breaking symmetries is the story of creation. Each shattered piece of that initial perfection gave rise to a new and interesting feature of our universe. The monolithic unity was replaced by a rich diversity of forces and particles. The blank canvas was now splattered with the foundational colors of reality. The universe was no longer perfect. But it was finally getting interesting. The imbalance of existence. Perhaps the most profound consequence of broken symmetry is the one that allows us to be here at all. The laws of physics, as we understand them, have a deep symmetry between matter and antimatter. For every particle, there should be an antiparticle with the same mass but opposite charge. When they meet, they annihilate each other in a flash of pure energy. So, according to the most symmetrical models, the Big Bang should have created matter and antimatter in perfectly equal amounts. For every electron, a positron; for every proton, an antiproton. As the universe expanded and cooled, these pairs should have annihilated each other completely, leaving behind a universe filled with nothing but light. No stars, no galaxies, and no life. A universe of perfect balance would be an empty one. And yet, here we are. We live in a universe completely dominated by matter. Every star, every galaxy, every planet we see is made of it. This glaring imbalance is one of the biggest mysteries in physics, known as the baryon asymmetry problem. To explain our existence, some process in the early universe must have broken this symmetry, showing a slight preference for matter over antimatter. In 1967, the physicist Andrei Sakharov laid out the 3 conditions needed for this to happen. First, the universe must go out of thermal equilibrium, which the rapid expansion of inflation provides. Second, there must be processes that violate certain fundamental symmetries, known as C and carbon monophosphide symmetry. Third, there must be a way to create more baryons, like protons, than antibaryons. Experiments have confirmed that the weak nuclear force does, in fact, violate these symmetries. This was a shocking discovery, flying in the face of long-held assumptions. While the violation we've measured isn't quite enough to explain the entire imbalance we see, it proves that nature has these asymmetries built right into its code. The leading theory is that in the universe's first moments, exotic heavy particles decayed in a way that wasn't perfectly symmetrical. Maybe for every 1 billion antiquarks they produced 1 billion and 1 quarks. A minuscule preference, but on a cosmic scale, it was everything. After the initial frenzy of creation and annihilation was over, this tiny surplus of matter was all that was left. This 1 in a billion rounding error is what we, and our entire observable universe, are made of. Our existence is the result of a cosmic flaw, a subtle imperfection in the laws of nature that allowed something to survive instead of nothing. The shattering of perfect symmetry wasn't just about making forces and particles, it was about choosing existence over annihilation. The beautiful, lopsided reality we live in is a testament to the creative power of a fundamental flaw. The canvas of imperfection, the breaking of symmetries gave us the stuff of the universe. But what about its structure? A universe filled evenly with matter would still be a pretty boring place. We needed cosmic architecture, galaxies, clusters, and the great voids between them. The blueprint for this grand design was laid down by another consequence of the initial shattering: the amplification of those quantum fluctuations. As we saw, inflation took tiny, random quantum jitters and stretched them to astrophysical scales. Once inflation ended, the universe was no longer perfectly smooth. It was seeded with tiny variations in density and temperature, incredibly small, on the order of 1 part in 100,000, but they were the gravitational seeds from which all structure would grow. We can see a direct snapshot of these initial imperfections by looking at the cosmic microwave background, or CMB. This is the oldest light in the universe, an afterglow of the Big Bang from about 380,000 years after it all began. When we look at the CMB with sensitive telescopes, it's almost perfectly uniform, at a temperature of about 2.725 Kelvin. This near uniformity is strong evidence for inflation. But when we crank up the contrast, we see a beautiful, mottled pattern of tiny temperature fluctuations. These are the anisotropies, the very imperfections that inflation predicted. The slightly hotter, denser spots in the CMB map are where gravity would begin its work. Over millions and billions of years, gravity took hold of this slightly uneven canvas. The regions that were infinitesimally denser had a slightly stronger pull. They began to draw in more matter. As they pulled in more matter, their gravity grew stronger, allowing them to pull in even more. It was a classic runaway effect. The rich got richer. The denser regions slowly collapsed to form the first stars and galaxies. These galaxies then pulled on each other to form massive clusters. The underdense regions, meanwhile, were emptied out, expanding to become the great cosmic voids that span hundreds of millions of light years. The entire cosmic web, the vast, filamentary structure of galaxies we see today, is a direct consequence of those minuscule quantum fluctuations from the universe's first moments. The existence of our own Milky Way galaxy, our solar system, our planet, can be traced back to a random quantum jitter that got blown up during inflation. We live in one of the lumpy bits. The birth of structure, the very architecture of the cosmos, is the ultimate expression of the universe's broken symmetry. The beauty of the flaw. We've journeyed from a state of abstract perfection to a cosmos teeming with structure. We've seen how a single, unstable point of symmetry shattered, cascading into a series of creative breaks that gave birth to the forces, particles, and imbalances that define reality. The universe is essentially telling us we've had it all backwards. We value perfection and see flaws as mistakes. But the story of the cosmos is one of a perfectly imperfect universe. Look at a snowflake. It appears to be a paragon of six-fold symmetry, yet no two are ever truly identical. Their beautiful, intricate patterns are a record of their unique journey through the sky, with tiny imperfections in their growth giving each one its character. A perfectly symmetrical snowflake would just be a boring hexagon. Or look at our own faces. We're built on a plan of bilateral symmetry, yet perfect facial symmetry is rare, and often looks strange or unsettling. The subtle asymmetries, a slightly higher eyebrow, a crooked smile, are what give a face its character and humanity. Even life itself thrives on imperfection. Evolution is driven by random mutations, errors in the replication of DNA. Most are useless, but every so often a random flaw provides a small advantage. Over eons, the accumulation of these advantageous imperfections is what allows life to adapt, diversify, and grow in complexity. Without imperfection, life would be static. The universe tells the same story on the grandest scale. The initial state of perfect symmetry was a state of pure, unrealized potential. It was beautiful in its mathematical elegance, but it was sterile. It was the shattering of that perfection that allowed for a universe of consequence, a universe where things can happen. The flaw in the vacuum created inflation. The flaw in the laws of physics created matter. The flaws in the distribution of energy created galaxies. This cosmic narrative suggests that imperfection isn't a bug, it's a feature. It is the engine of creation. Flaws are what make things interesting, what allows for change, growth, and evolution. A universe without them would be a universe without a story, without time, without us. Exploring these grand narratives, from the tiniest quantum fluctuation to the largest cosmic structures, is what drives our curiosity about the universe. It's a journey to understand not just what's out there, but what it means for us to be here. If you find this journey as fascinating as I do, consider subscribing for more explorations into the cosmos and the beautiful, broken laws that govern it. Conclusion. So, what was the final day of perfect symmetry? It was the final moment of non-being. It was the last instant before time had meaning, before space had texture, before existence had chosen a side. The violent, beautiful shattering of that flawless state wasn't an act of destruction, but the ultimate act of creation. It replaced a single, sterile perfection with an infinity of beautiful, intricate flaws. We are the living, thinking descendants of that primordial imperfection. Our existence is a paradox, a temporary island of complexity that arose from a fundamental break in the universe's initial symmetry. We are made from the rubble of a fallen perfection. And when we look up at the night sky, at the scattered, asymmetrical beauty of the stars and galaxies, we are seeing the magnificent, enduring legacy of that single, creative flaw. The universe is not perfect. And that is the most beautiful thing about it. If perfect symmetry is a state of non-existence, what does that say about our own striving for perfection? Perhaps the most profound truth is that beauty isn't found in the flawless ideal, but in the intricate, messy, and magnificent reality that emerges when that ideal is broken. The universe's first mistake created everything. Imagine a universe born not into chaos, but into a state of profound, absolute perfection. Not the perfection of a starry night, but something deeper. A silent, featureless sea of energy, infinitely hot and dense, and perfectly, flawlessly uniform. In this early cosmos, every particle was identical to every other. Every point in space was indistinguishable from the next. There was no up or down, no here or there. It was a state of perfect symmetry, a masterpiece of balance. And there, it could have remained, in eternal, unchanging stillness. A universe with a magnificent birth but no future. No stars could form, no planets could gather, no life could emerge to witness it. It was a paradise of stagnation, a perfect prison of sameness. And yet, we are here. Our existence is owed not to that perfection, but to a series of magnificent errors that broke it. A single, cosmic flaw, a tiny break in the sublime balance, is the reason anything exists at all. That imperfection became the trigger for matter, for structure, for complexity, and ultimately, for us. This is a journey to the dawn of time, to witness a universe of impossible balance, and to see the moment it all went beautifully, necessarily wrong. We will discover how a single act of broken symmetry became the blueprint for all of creation. Before we can understand the flaw, we must first appreciate the perfection it broke. The idea of a perfectly symmetric beginning isn't just a poetic notion, It's a cornerstone of modern physics. In nature, systems tend to seek states of symmetry. They represent the path of least resistance, a state of minimal energy and maximum stability. Think of a crystal, where atoms arrange themselves into a repeating lattice. Or a soap bubble, which pulls itself into a perfect sphere, the shape containing the most volume for the least surface area. On a fundamental level, the universe favors balance. This preference is so profound that it's woven into the fabric of physical law. A principle discovered by the brilliant mathematician Emmy Noether reveals a quiet, deep connection. For every continuous symmetry in nature, there is a corresponding conservation law. The fact that the laws of physics are the same today as they were yesterday, a symmetry in time, is why energy is conserved. The fact that the laws are the same everywhere, a symmetry of translation, is why momentum is conserved. In the beginning, the universe was ruled by a set of ultimate symmetries, leading to a state of profound stillness. Let's travel back to the first microsecond. The universe was a cauldron of unbelievable heat, a state known as the quark-gluon plasma. In this primordial soup, quarks and gluons, the building blocks of matter, were so energetic they couldn't bind together. They existed as a free, indifferentiated, and perfectly symmetric sea. Every quark was functionally identical to every other. The forces that governed them were unified. There was no structure, no identity. Everything was interchangeable. Imagine an infinite, still ocean of liquid glass, heated to a point of absolute uniformity. A cup scooped from one part would be indistinguishable from any other. It is beautiful in its featurelessness, but nothing can happen there. It has no story to tell. This was the universe in its state of grace, a perfect, sterile kingdom of sameness. For any story to begin, this perfect kingdom had to fall. The symmetry had to break. In the searing heat of the newborn cosmos, this state of perfect symmetry was stable. But the universe does one thing relentlessly: it expands. And as it expands, it cools. As the temperature dropped past critical thresholds, the perfect balance became unstable. The universe was like a pencil balanced on its point, a state of perfect symmetry, yet exquisitely fragile. The slightest nudge, and it will fall, choosing one direction over all others and breaking the symmetry forever. The cooling of the universe was that nudge. And in a series of breathtaking moments, the pencil began to fall. The first of these cosmic errors concerned the nature of substance itself. In the initial symmetric state, all fundamental particles were massless. They were pure energy, zipping about at the speed of light. But a fraction of a second after the Big Bang, as the universe cooled to about a quadrillion degrees, a new phenomenon occurred. A theoretical energy field that permeates all of space, now known as the Higgs field, transitioned. It switched on. Before this moment, the Higgs field was in a symmetric state, with a value of 0 everywhere. But as the universe cooled, it dropped into a new, lower energy state with a non-zero value. This is called spontaneous symmetry breaking. Imagine a vast, perfectly flat plain of snow. Suddenly, a trough appears across the entire landscape. Particles moving across this landscape are now affected. Some, like photons, are unaffected and continue on, massless. But other particles, like quarks and electrons, interact with this new background. They get stuck, or dragged, by it. This interaction is what we perceive as mass. Suddenly, the universe had distinction. It had heavy particles and light particles. The perfect interchangeability was gone. A hierarchy was born. It was the first act of differentiation, the first mistake that gave substance to the void. At the same time, another critical symmetry was breaking. In the primordial heat, two of the four fundamental forces, the electromagnetic force and the weak nuclear force, were one and the same, a unified, electroweak force. But as the universe cooled and the Higgs mechanism kicked in, this unified force froze out and split into the two distinct forces we know today, much like how steam, a single substance, condenses into both liquid water and solid ice. The electromagnetic force became the force of light and chemistry. The weak nuclear force became the engine of radioactive decay, essential for powering stars over billions of years. Without this divorce between the forces, the chemistry required for life would be impossible. The universe was creating new rules for itself. Yet, even with mass and new forces, the cosmos was on a path to oblivion. The Big Bang should have created matter and antimatter in exactly equal amounts. When matter and antimatter meet, they annihilate into pure energy. In a perfectly symmetric universe, every particle would have found a partner, and the cosmos would have dissolved into a featureless sea of light. Nothing would be left. But this is not what happened. The laws of physics, it turns out, are not perfectly balanced. This slight asymmetry is known as CP violation. It is a subtle flaw in the rules, a microscopic preference for matter over antimatter. And it had the most profound consequence imaginable. In the great annihilation that followed the Big Bang, for every billion pairs of matter and antimatter particles that destroyed each other, one single, solitary particle of matter was left over. 1 in a billion. It was a cosmic rounding error. A minuscule imperfection. But that leftover debris is everything. It is every star, every galaxy, every planet. You are made of the survivors of a cosmic war that should have had no winner. Your existence, and the existence of the entire material universe, is owed to this crucial imbalance. The universe had survived its own annihilation, but it was still just a hot, uniform fog. For 380,000 years, the cosmos remained a glowing haze, so dense that light could not travel freely. Then, as the relentless expansion continued to cool the cosmos, another threshold was reached. At a temperature of about 3000 Kelvin, the universe was cool enough for atomic nuclei to finally capture electrons, forming stable, neutral atoms. This event is called recombination. In a cosmological instant, the fog cleared. With the electrons bound into atoms, photons were suddenly free to travel unimpeded. The universe became transparent for the first time, releasing a flash of light that has been traveling ever since. Today, we detect that light as the cosmic microwave background, CMB, the oldest light in the universe. It is a baby picture of the cosmos, a snapshot of the moment it emerged from its opaque infancy. And what does this picture show? A universe of almost impossible uniformity. When we look at the CMB, we see that its temperature is the same everywhere we look, with tiny variations of only about 1 part in 100,000. This astonishing smoothness is the ultimate echo of that initial perfect state. But it is not perfectly smooth. And in its tiny imperfections, the next chapter of creation was written. Embedded in the CMB's glow are minuscule temperature fluctuations, tiny patches infinitesimally hotter or colder than the average. These are the fossilized remnants of quantum fluctuations from the very first moments of existence. According to the theory of cosmic inflation, the universe underwent a period of hyper-expansion, stretching these microscopic, unpredictable jitters of quantum reality to macroscopic cosmic scales. These tiny variations in temperature correspond to tiny variations in density. The slightly cooler spots were regions where matter was just a fraction of a percent denser than average. These were the seeds of all structure. With these seeds planted, a quiet, patient force took over as the master architect of the cosmos, gravity. The regions that were already slightly denser began to exert a slightly stronger gravitational pull. Over millions of years, they slowly siphoned matter from the less dense regions. The tiny fluctuations began to grow. Over hundreds of millions of years, this process sculpted the universe. The nearly uniform soup of gas coalesced into vast, interconnected structures. Immense, empty voids opened up, and in between them, matter accumulated into long, intricate filaments and dense knots. This is the cosmic web, its pattern a direct, gravitational amplification of those initial quantum seeds. The web-like distribution of galaxies is a map of quantum mechanics written across the sky. Inside the densest knots, gravity continued to pull gas into ever tighter balls. As the pressure and temperature at their cores mounted, a new threshold was crossed. Hydrogen atoms fused, creating helium and releasing a tremendous burst of energy. The first stars ignited, flooding the dark universe with light. Inside these stellar furnaces, new elements were forged: carbon, oxygen, silicon, iron. When massive stars ended their lives, they exploded as supernovae, scattering these elements across space, enriching the gas clouds from which future generations of stars and planets would be born. The vast clouds of gas that formed galaxies possessed a slight, residual spin. As they collapsed, this spin was magnified, just as an ice skater spins faster when she pulls her arms in, causing the clouds to flatten into vast, rotating disks. The beautiful spiral galaxies, including our own Milky Way, are a direct consequence of this process, systems of immense order born from the breaking of perfect spherical symmetry. We have followed a chain of events we have called mistakes. But it becomes clear, when we look closer, that this word does not quite fit. What we've been calling a flaw is, in fact, a necessary feature of a complex universe. Perfection, in the sense of absolute uniformity, is a creative dead end. Asymmetry and imperfection are the engines of change. Look at biology. The principle of perfect symmetry is an idealized blueprint. In reality, nature is full of advantageous asymmetries. Your own heart is situated on the left side of your chest. The two hemispheres of your brain are specialized for different functions. Life doesn't just tolerate imperfection, it thrives on it. This principle extends to our sense of beauty. In the Japanese art of kintsugi, broken pottery is repaired with gold lacquer. The philosophy is not to hide the break, but to celebrate it, acknowledging that the object's history makes it more beautiful, not less. A snowflake begins with perfect hexagonal symmetry. But as it tumbles through the atmosphere, its journey is unique, causing each of its arms to grow in a slightly different way. Their breathtaking beauty comes not from their initial, sterile symmetry, but from the unique imperfections gathered on their journey. Now, let's turn this lens back to the cosmos. The universe is not a pristine crystal. It is a work of kintsugi on a cosmic scale. The 1 in a billion imbalance that allowed matter to exist is the golden lacquer that fills the cracks of the Great Annihilation. The tiny quantum fluctuations that broke the uniformity of the CMB are not defects. They are brushstrokes giving texture to a blank canvas. Without them, the universe would be a thin, cold gruel of hydrogen, devoid of galaxies, stars, or planets. What we called a mistake was, perhaps, a choice. The universe chose complexity over simplicity. It chose the vibrant, messy path of becoming over the sterile, eternal perfection of being. If this kind of calm exploration into the grand questions of our reality helps you unwind, consider subscribing and becoming part of this community of cosmic explorers. We journey into these great mysteries, striving to understand our place within this grand cosmic story. And I have a question for you to ponder. What other mistakes or imperfections, either in the cosmos or here on Earth, do you find to be unexpectedly beautiful or creative? Let's discuss the power of the flaw in the comments below. We began our story with an image of a perfect universe, a silent, unchanging, and ultimately empty state. We have journeyed 13.8 billion years to arrive here, in a universe teeming with structure, complexity, and life. And the thread connecting that beginning to our present has been a series of profound and creative breaks from that initial perfection. A cascade of symmetry-breaking events transformed the stillness. The Higgs mechanism shattered the uniformity of particles, giving them mass. The electroweak force fractured, giving rise to the distinct laws that govern the shining of stars and the chemistry of life. The most crucial error, CP violation, allowed a tiny fraction of matter to survive, providing the raw material for everything we see. And finally, primordial quantum jitters, stretched to cosmic proportions, gave gravity the instructions it needed to build the first galaxies. Each of these events can be seen as a deviation from a simpler set of rules. But they were not acts of destruction. They were acts of creation. Every star that burns is a testament to the beauty of broken symmetry. Every spiral galaxy, a monument to the creative power of imperfection. We, as conscious beings, are the ultimate expression of this principle. We are not merely observers of this wonderfully flawed universe, we are its living embodiment. Our very atoms are the recycled dust of stars, born from the initial asymmetry that allowed matter to be. We are the improbable, beautiful consequence of the universe's foundational imbalances. Perhaps, then, the final reframing is this: the mistake was never a mistake at all. The potential for asymmetry was always there, latent within the laws of physics, waiting for the right conditions to unfold. The universe did not fall from a state of grace. It awoke from a state of slumber. The flaw, it seems, wasn't an error in the blueprint. The flaw was the blueprint. And the result is a universe that is not perfect, but something far more profound. It is interesting, and it is home, why the universe had to break to exist. Look around you, at the device in your hands, the room you're in. Look up at the sky, at the sun and the moon, and the impossibly distant stars. All of it, every atom and every galaxy, is a quiet survivor. A trace of a possibility that should have vanished in a flash of light. Everything we can see, and everything we cannot, exists because of a fundamental departure from perfection. A subtle break in an otherwise pristine design of reality. Without this imperfection, this tiny shift in the rules, the universe would be a featureless and empty void. A sea of pure energy with nothing in it. The story of our existence, then, is not one of serene, flawless creation. It is the story of a fundamental transition. It's the story of how the cosmos had to shift, to shatter its own symmetry, in order to escape a prison of nothingness and allow for the existence of, well, everything. The universe was almost a prisoner of its own perfection. In the very first moments of time, it was governed by a set of rules so balanced, so symmetrical, that it seemed destined to be a forever empty expanse. No stars, no galaxies, and no life. For something to exist, that symmetry had to give way. And in a quiet, cataclysmic instant, it did. This is the story of the cosmic imbalance that allowed everything to emerge from nothing. To understand this shift, we first have to understand the prison it unlocked. It's a prison built from one of the most beautiful ideas in physics, symmetry. In physics, symmetry is more than just the pleasing pattern of a snowflake. It means that if you change something about a system, the laws governing it remain the same. Think of it this way. In a space with no gravity, no up or down, a thrown ball travels in a straight line forever. If you move to a different spot and throw the ball again with the same force, it behaves in exactly the same way. This is called translational symmetry. The laws of physics don't change based on your location. If you rotate your experiment, the outcome is also the same. That's rotational symmetry. These are not just abstract ideas, they are the bedrock of our reality. The mathematician Emmy Noether proved that for every continuous symmetry like this, there is a corresponding law of conservation. The conservation of momentum comes from translational symmetry. The conservation of angular momentum comes from rotational symmetry. And the conservation of energy comes from the fact that the laws of physics do not change over time. In the very beginning, for a sliver of a moment after the Big Bang, the universe was the most symmetrical place it has ever been. The energies were so extreme that the four fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, are thought to have been merged into a single, unified superforce. The particles that emerged were massless, all moving at the speed of light. The rulebook was pristine and perfectly balanced. But this perfect balance held a profound consequence. The same laws that dictated the creation of particles also dictated the creation of their twins, antiparticles. The standard model of cosmology suggests that the Big Bang should have produced matter and antimatter in equal amounts. For every electron with its negative charge, a positron was born with a positive charge. For every quark, an antiquark. They were perfect mirror images, created in inseparable pairs. And this is where the walls of the prison begin to appear. When a particle of matter meets its antiparticle, they annihilate. They vanish in a burst of pure energy. Picture that infant universe, an unimaginably hot, dense soup of energy, constantly creating pairs of particles and antiparticles. In a perfectly symmetric universe, for every billion pairs created, a billion pairs would collide and annihilate. Every single particle would eventually find a partner. The result would have been total, complete annihilation. As the universe expanded and cooled, this process would continue until all matter and antimatter wiped each other out, leaving behind only a diffuse bath of light. The universe would become a vast, empty, and silent graveyard of possibilities. No atoms, no stars to forge heavier elements, no planets, and no life. This is the prison of perfection. A universe governed by flawless, symmetrical laws is a universe destined to be empty. For anything, for you, to exist, this perfect symmetry had to be broken. The scales had to be tipped. Somehow, out of the cosmic fire, a survivor had to emerge. For every billion annihilations, one single particle of matter had to be left over, with no antimatter partner to destroy it. This tiny remnant is the foundation of everything we see. Our existence is proof that the universe is not perfect. It is proof of a cosmic imbalance. The question is, how did this happen? What mechanism could be powerful enough to tilt the scales of creation itself? The answer lies in the subtle clues left behind from that very first moment. The evidence of this imbalance is our own existence. We are here. Therefore, the perfect symmetry between matter and antimatter must have been broken. Scientists call this the baryon asymmetry problem, which is a thoughtful way of asking, where did all the antimatter go? For a long time, one possibility was that it was still out there somewhere, hiding in anti-galaxies far from our own. But if that were true, the boundaries between matter and antimatter regions would be sites of constant annihilation, producing a detectable glow of gamma rays. We've looked. That glow isn't there. The observable universe is made, overwhelmingly, of matter. So, a genuine imbalance must have occurred in the beginning. In 1967, the physicist Andrei Sakharov outlined three conditions, three ingredients, necessary to explain how this could happen. Think of it as a recipe for existence. First, you need a process that violates something called baryon number. Baryons are a family of particles including the protons and neutrons in your body. Baryon number is like a census. You add up the baryons, subtract the antibaryons, and you get a number that, according to most laws, should never change. To create a surplus of matter, some process in the early universe must have been able to change this number. Second, the universe must violate something called carbon monophosphide symmetry. This combines two symmetries. See symmetry. If you swap a particle with its antiparticle, the physics are the same, and P symmetry. If you view a process in a mirror, the mirror image is also possible. For a long time, physicists thought these symmetries were absolute. But in 1964, an experiment showed that for certain interactions, the universe does have a slight preference. It violates carbon monophosphide symmetry. This discovery was monumental. It proved the laws of physics were not entirely ambidextrous. There is a subtle difference in how matter and antimatter behave. Sakharov realized this was a key ingredient. Without this built-in bias, Any process creating an extra baryon would be balanced by another creating an extra anti-baryon, and you'd end up with nothing. The third condition is that these processes must happen out of thermal equilibrium. In a perfectly stable system, any reaction that creates matter happens at the same rate as the reverse reaction that destroys it. You need a period of rapid change, like the universe's frantic expansion and cooling, to freeze in the imbalance before it could be erased. So we have the conditions. But what actually caused all of this to happen? The answer seems to lie in a deeper kind of symmetry breaking, a phenomenon known as spontaneous symmetry breaking. This is one of the most powerful ideas in modern physics. It says that even if the underlying laws of a system are perfectly symmetric, its most stable state, its lowest energy state, doesn't have to be. The symmetry is still there in the laws, but it's hidden in the outcome. The classic analogy is to imagine a ball perfectly balanced at the peak of a hill. The setup is symmetric, but this state is unstable. The slightest nudge will cause the ball to roll down into the valley below. Once it settles, it has chosen a specific direction. The initial symmetry is gone. The ball is here, not there. The symmetry of the system has been spontaneously broken. The laws are still symmetric, but the outcome is not. Physicists believe this is what happened to the entire universe. In the searing heat of the first moments, the universe was in a state of high energy, perfect symmetry, a false vacuum. It seems stable, but it isn't the true lowest energy state. Then, as the universe expanded and cooled, it reached a critical temperature. About a trillionth of a second after the Big Bang, the universe underwent a cosmic phase transition. The fabric of space itself froze into a new, lower energy state. It rolled down the hill. And in doing so, it broke the symmetry. This event was driven by a field that permeates all of space, the Higgs field. In the hot early universe, the Higgs field was in a symmetric state. But as the universe cooled, it settled into a new state. This spontaneous breaking of what's known as electroweak symmetry was the cataclysmic event that changed everything. Suddenly, the unified electroweak force split into the two distinct forces we know today: the electromagnetic force and the weak nuclear force. And most importantly, this is how particles got their mass. Particles that interacted strongly with this newly settled Higgs field gained a lot of mass. Others that interacted weakly gained a little. The world of identical, massless particles was gone. In its place was a diverse zoo of particles with different masses and properties. The universe now had texture. It had complexity. This spontaneous breaking of symmetry is the break that allowed for existence. Not only did it give particles the mass they needed to form structures, but it is also connected to the problem of the matter-antimatter imbalance. The complex interactions tied to the Higgs mechanism provide a source of CP violation. However, the amount we've measured in our standard model is not nearly enough to explain the universe we see. This suggests that the full story requires new physics, perhaps new particles or forces, that were at play during this critical time. The breaking wasn't a flaw, it was a feature. A necessary step. The perfect, symmetric state was a dead end, destined to fall. And in its fall, in that spontaneous choice of direction, it unlocked the potential for everything that would ever be. It created a universe not of sterile balance, but of messy, complex, and beautiful imperfection. The imperfection that allows us to be here. The breaking was complete. The perfect symmetry of the infant cosmos was shattered. In its place was a universe with a crucial surplus of matter, and where, for the first time, particles had mass. These were the two keys needed for the next chapter of cosmic history. They were the seeds from which everything we see would eventually grow. Without mass, particles like electrons and quarks would forever move at the speed of light, unable to settle down or bind together. A universe of massless particles is one where nothing ever clumps together. It's a universe without atoms, stars, or galaxies. But the Higgs mechanism changed the rules. By giving particles mass, it gave gravity something to grip onto. At the same time, we had the other key ingredient: the tiny 1 in a billion surplus of matter left over from the Great Annihilation. Let's paint a picture of the universe in the aftermath. It's about 1 microsecond old. As it cools, the strong nuclear force confines the surviving quarks into the particles Sakharov was concerned with, baryons. For the first time, stable protons and neutrons form. The universe is now a hot, dense plasma of protons, neutrons, and electrons, swimming in a sea of light. It's still too energetic for atoms to form. Any electron that tries to bind with a proton is immediately knocked away. But the universe continues its relentless expansion and cooling. For the next few minutes, in a period called Big Bang nucleosynthesis, the first atomic nuclei are forged. Protons and neutrons stick together. Hydrogen nuclei fuse to form deuterium, and then helium. By the end of this period, the cosmic alchemy is mostly over. The matter in the cosmos is now roughly 75% hydrogen nuclei and 25% helium nuclei. This prediction is one of the great triumphs of the Big Bang theory. When we look at the oldest gas clouds in the universe, the amounts of these elements match the predictions with stunning accuracy. It's a powerful sign that we are on the right track. And yet, the universe is still an opaque fog. Free electrons constantly scatter light, so it cannot travel far. This continues for another 380,000 years. Finally, the universe cools enough for electrons to be captured by the hydrogen and helium nuclei, forming the first stable, neutral atoms. This event is called recombination. And with the electrons now bound, the photons are suddenly free. For the first time, the universe becomes transparent. The light trapped within the plasma is released, beginning a journey through space that continues today. That light is the cosmic microwave background, the CMB. It's the afterglow of the Big Bang. When we build detectors to see this light, we are looking at a baby picture of the universe. And within that picture, we see the seeds. The CMB is not perfectly uniform. There are tiny variations in its temperature, about 1 part in 100,000. These correspond to slight differences in density in the primordial soup. Some regions were infinitesimally denser than others. These tiny seeds of structure are where gravity takes center stage. Over millions of years, the slightly denser regions begin to pull in more matter. The rich get richer. For hundreds of millions of years, the universe enters what is known as the cosmic dark ages. The initial light has faded, and the first stars have not yet ignited. But inside the densest regions, gravitational collapse continues. The gas clouds become smaller and hotter. Eventually, in their hearts, the pressure and temperature reach a critical point, and nuclear fusion ignites once more. The first stars are born. These were monsters, perhaps tens to hundreds of times more massive than our Sun. They burned through their fuel in just a few million years, ending in colossal supernova explosions. These explosions seeded the cosmos with heavier elements, carbon, oxygen, iron, forged in their cores. These are the raw materials for the next generation of stars, for planets, and for life. Those first stars formed clusters, which merged to form the first galaxies. And those galaxies grew over billions of years into the great cosmic web we see today. The entire intricate structure of the universe is the result of those tiny density fluctuations, amplified by gravity, acting on matter that was only there because of an ancient imbalance. Every star and every galaxy is a direct consequence of the universe breaking its own perfect symmetry. It all started with a single departure from perfection. And from that one act, the entire complex structure of the cosmos was born. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near a city, a forest, or somewhere quiet in between, Feel free to share where you're watching or listening from. This grand narrative is a powerful story. But in science, a story is only as good as its evidence. We have been gathering clues from the cosmic dawn for decades. The first, most profound piece of evidence is the sky itself. The cosmic microwave background. Its existence is a confirmation of the Big Bang model, but it's the tiny imperfections, those temperature fluctuations, that tell a deeper story. The specific pattern and size of these fluctuations perfectly match what we would expect in a universe composed of the specific mix of matter and energy our models predict. Then there is the evidence for the matter-antimatter asymmetry. The theory of Big Bang nucleosynthesis is incredibly sensitive to the initial amount of protons and neutrons. The observed abundances of hydrogen, helium, and lithium only make sense if the universe began with that specific 1 in a billion surplus of matter. What about the cause? The breaking of CP symmetry is not just a theoretical requirement, it is an experimentally verified fact. Following the 1964 discovery, experiments at facilities like CERN have meticulously studied particles like B-mesons. They have confirmed with exquisite precision that the standard model of particle physics contains CP violation. We have seen, unequivocally, that nature does treat matter and antimatter differently. However, there's a twist. The amount of CP violation we've measured is not enough. It's too small, by many orders of magnitude, to explain the colossal matter-antimatter imbalance we observe. This is one of the biggest unsolved mysteries in physics. It tells us that our story is incomplete. There must be other, undiscovered sources of this asymmetry, likely involving new particles or forces beyond our current understanding. And finally, what about the central act of the story? The spontaneous breaking of symmetry by the Higgs field? The most celebrated piece of evidence came in 2012. Two independent experiments at CERN's Large Hadron Collider announced the discovery of a new particle, the Higgs boson. The boson is an excitation of the field. Finding the particle was proof that the field itself is real. Its discovery was the triumphant confirmation of the mechanism that gives fundamental particles their mass. The properties of the Higgs boson have so far matched the predictions of the Standard Model perfectly. But physicists continue to study it with intense scrutiny, looking for any tiny deviation that might point to a deeper theory. From the faint glow of the CMB to the subtle decays of subatomic particles, the evidence is overwhelming. The universe we inhabit is the product of a series of breaks from a more perfect, more symmetric past. The clues are all around us, written into the fabric of reality. We began with a simple observation: we exist. From that fact, we have journeyed back to the first moments of time to uncover a truth. Our universe, in all its sprawling glory, is the result of a fundamental imperfection, a departure that allowed something to escape the prison of nothingness. The initial state of the cosmos, a realm of perfect balance, was a recipe for an empty existence. But that perfection was unstable. In a pivotal moment, a trillionth of a second into its life, the universe broke. A fundamental field settled into a new state, shattering the elegant symmetry of the forces of nature. This single act had profound consequences. It endowed particles with mass, allowing gravity to begin its slow work of building structure. It created a subtle but crucial difference between matter and antimatter, allowing a tiny fraction of matter to survive. From that 1 in a billion survivor, everything else followed. The formation of protons and neutrons. The forging of the first elements. The slow collapse of gas clouds into the first stars. The gathering of stars into galaxies and galaxies into the vast cosmic web. The story of the cosmos is the story of symmetry breaking. Each break peeled back a layer of simplicity and revealed a new layer of complexity. We are, in the most literal sense, the children of a broken symmetry. And yet, the story is not over. We know the break happened, but we don't know all the details. The Standard Model, for all its success, cannot fully account for the matter-antimatter asymmetry. This points to new physics, to unknown particles and forces waiting to be discovered. The greatest questions remain. So the next time you look up at the night sky, remember what you are seeing. You are not witnessing an act of perfect creation. You are witnessing the beautiful, sprawling aftermath of a cosmic transition. A universe that had to break its own perfect laws, that had to embrace imperfection, in order to exist at all. And in that imperfection, it found the freedom to create everything. Science just found the first flaw in reality. Every structure has a blueprint. The house you live in. The device you're watching this on. Even you. For decades, we thought we had the blueprint of the universe itself. A moment of perfect, brilliant symmetry at the dawn of time. An event we call the Big Bang. We even have a picture of it. A photograph of creation taken when the cosmos was just 380,000 years old. It showed a universe that was almost impossibly uniform, a testament to a perfect beginning. But what if that blueprint is wrong? What if, deep inside this picture of perfection, science is staring at the first flaw? Not just an error in our math, but a fundamental break in the fabric of reality itself. There's a tiny asymmetry hidden in the oldest light in the universe. A crack in the cosmic blueprint that could rewrite the entire story of how everything, and everyone, came to be. This is the story of how a single imperfection may have become the architect of all existence. For one fleeting moment, the universe was perfect. A state of such pure symmetry and energy that the laws of physics as we know them hadn't even been born yet. Then, in less than a blink of an eye, it all changed. That perfection shattered. This is the story of that first break, a story that begins not with a bang, but with a flaw. And to get it, we have to look at the most perfect picture ever taken. The blueprint of perfection. To get your head around the scale of this, we first need to understand the masterpiece it threatens to mess with, our standard model of cosmology. It's called lambda CDM, and it's one of the most successful theories in all of science. It tells a story that kicks off 13.8 billion years ago. Now, forget the popular image of a bomb exploding in an empty room. The Big Bang wasn't an explosion in space. It was the beginning of space itself. Every single point in our observable universe was once the asterisk same point, an infinitely dense, infinitely hot singularity. From that one point, space started expanding, carrying energy and the stuff of matter along for the ride. In the very first sliver of a second, a slice of time so small it makes a nanosecond look like an eternity, the universe went through a wild, exponential growth spurt called cosmic inflation. In just 10 to the minus 32 seconds, the universe blew up by a factor of at least 10 to the 26. That's like a single atom suddenly swelling to the size of a galaxy. Inflation was a brilliant theory because it solved a bunch of cosmological puzzles, but its biggest prediction was about smoothness. This hyper-expansion would have stretched the fabric of spacetime, ironing out any wrinkles. It predicted the early universe should be almost perfectly homogeneous, looking the same everywhere, and isotropic, looking the same in every direction. After inflation, the expansion cooled its jets, and the universe was left as a hot, dense, foggy soup of protons, neutrons, and electrons, all tangled up with a sea of light particles, photons. For 380,000 years, that's how things were. Light was trapped, bouncing off free electrons like a pinball. The universe was a glowing, impenetrable cloud. But as it kept expanding, it cooled down. Finally, it hit a critical temperature, about 3000 Kelvin. At that point, protons and electrons were slow enough to hook up, forming the first neutral atoms, mostly hydrogen and helium. This event is called recombination. And it changed everything. Suddenly, with all the free electrons locked away in atoms, the photons were set free. For the first time, the universe became transparent. The light that was right there at that moment could now travel across the cosmos, forever. And that ancient light, released 13.8 billion years ago, is still traveling today. It's been stretched out by the universe's expansion, its wavelength pulled from visible light all the way into the microwave part of the spectrum. This is the cosmic microwave background, or CMB. It is, literally, the oldest light in the universe. When astronomers Arno Penzias and Robert Wilson first stumbled upon it in 1964, it was just a faint, uniform hiss coming from every direction. It was the afterglow of creation, the echo of the Big Bang. And it was incredibly uniform. In 1989, NASA's COBE satellite mapped it and confirmed the theory with a triumphant roar. The CMB's temperature was stunningly consistent across the whole sky. 2.725 Kelvin, with variations of only 1 part in 100,000. It was the baby picture of the universe, and it looked perfect. The smoothness was a huge win for the inflation model. For a while, it seemed like our cosmic blueprint was complete. The story was neat. A perfect, symmetric start, smoothed by inflation, leading to the universe we have today. But that picture of perfection? It was an illusion. A closer look was about to show that the canvas wasn't nearly as clean as we thought. A crack in the canvas. The success of COBE led to even better instruments, like WMAP and the European Space Agency's Planck satellite, which gave us the most detailed map of the CMB ever made. These missions confirmed the temperature wasn't perfectly uniform. It was speckled with tiny hot and cold spots, called anisotropies. Okay, you have to understand that these spots, on their own, are not the problem. In fact, our model demands they exist. These tiny temperature wiggles, differences of just a few millionths of a degree, are the fossilized imprints of quantum jitters from the inflation era, stretched to cosmic size. The model says these tiny temperature differences match up with tiny density differences in the early universe. The slightly hotter, less dense spots would grow into the huge, empty voids of space. The slightly colder, denser spots would become gravitational seeds. Over billions of years, these seeds would pull in more and more matter, growing into the cosmic web of galaxies, stars, and planets. You, me, this planet, we are all descendants of those tiny, random fluctuations in the infant universe. So if the spots are supposed to be there, where's the flaw? The flaw isn't that there are spots on the baby picture. The flaw is the asterisk pattern they make. A pillar of modern physics, the cosmological principle, says the universe on the largest scales should be isotropic, the same in all directions. This means the hot and cold spots in the CMB should be totally random. There shouldn't be any special directions or large-scale patterns. But as scientists looked closer at the WMAP and Planck data, they found things that just shouldn't be there. Faint, large-scale features that seemed to break this fundamental rule of randomness. They found anomalies. The most famous one has been given the ominous nickname, the axis of evil. When you break down the CMB patterns, the two largest scale patterns, the quadrupole and the octupole, are mysteriously aligned with each other. The odds of that happening by chance are slim. But the truly weird part? This axis also seems to be aligned with the plane of our own solar system. Suddenly, our little corner of the universe seemed to have a special connection to the largest structures in existence. This flies in the face of the Copernican principle, the idea that we're not in a special or privileged spot in the cosmos. Then there's the CMB cold spot. This is a huge patch of the sky, about 20 times wider than the full moon, that is bizarrely cold. It's not just a little cold, it's about 70 microkelvin cooler than the average, with some points dipping to 140 microkelvin colder. The typical temperature variation is only about 18 microkelvin, making this spot a massive outlier. The standard model says a spot this big and this cold is exceptionally unlikely to happen by chance. Some estimates put the odds at less than 1 in 1,000. And there's more. A weird hemispherical asymmetry, where the temperature variations on one half of the sky are slightly stronger than on the other. Plus, a lack of power in the very largest patterns compared to what the model predicts. Taken one by one, you could maybe write these off. But together, they start to paint a pretty worrying picture. As the Planck team itself said, it's not clear if these are just statistical flukes or a sign of new physics. Now, let's take a step back. The standard model, lambda CDM, is incredibly successful at explaining almost everything else about the universe. These anomalies are tensions, not total refutations. Many cosmologists think they probably are just statistical flukes, unlikely, sure, but not impossible in the cosmic lottery. Or maybe they're just some subtle contamination from our own galaxy that we haven't managed to scrub out of the data yet. But what if they're not? What if these weird alignments and cold spots are real? What if they're the first signs that our perfect blueprint for creation is not just imperfect, but fundamentally flawed? This possibility has thrown open the doors to a whole new world of investigation, pushing scientists to find an explanation, no matter how strange. The search for an explanation. Faced with these weird patterns, the scientific community did what it does best: it started digging. The search for answers falls into three main buckets, ranging from the pretty normal, to the slightly strange, to the truly mind-bending. The first, most conservative, idea is that the anomalies aren't cosmic at all. They're either a statistical fluke or a mistake in the data. The fluke argument is simple. Unlikely things happen. The odds are low, but not zero. Maybe we just live in a universe where the cosmic dice came up weird. It's not a satisfying answer, but it's scientifically plausible. We only have one sky to look at, so it's not like we can rerun the experiment. The mistake explanation is a bit more complicated. That light from the CMB traveled for 13.8 billion years to get to us. On the way, it passed through tons of galaxies and dust clouds. Scientists work incredibly hard to map and subtract these foregrounds to get a clean picture, but it's possible some junk is left over, creating the illusion of these patterns. That alignment with our solar system definitely points a finger of suspicion at some local effect we haven't corrected for. The second path explores ideas within known physics. The leading hypothesis for the CMB cold spot is a great example: the Eridanus supervoid. A supervoid is exactly what it sounds like: a gigantic, almost unbelievably empty region of space, with way fewer galaxies, less gas, and less dark matter than average. In the late 2000s, astronomers found a massive supervoid, maybe 1 billion light-years across, in the exact same direction as the cold spot. Coincidence? Probably not. An effect called the integrated Sachs-Wolf (ISW) effect gives us a physical link. Our universe's expansion is accelerating because of dark energy. So, as photons from the CMB pass through a giant void, they lose a bit of energy. When they come out the other side, the universe has expanded, and the void has flattened out a bit. They don't regain all the energy they lost, so they come out slightly colder, making that patch of sky look colder to us. The Eridanus supervoid is one of the largest structures ever found, and it sits right between us and the cold spot. Recent analysis from the Dark Energy Survey confirmed the void's existence and profile, providing strong evidence that the ISW effect from this void is responsible for a good chunk of the cold spot's temperature drop. Research in 2024 has continued to build this case. It's a powerful, elegant explanation using physics we already know. Still, some debate remains. Some studies suggest the void isn't quite big or empty enough to explain the entire temperature drop, leaving the door open for something more primordial. This brings us to the third, most speculative path, the one that leads to the title of this video. What if the anomalies aren't flukes or mistakes or voids? What if they're primordial? What if they are the direct signature of a flaw in the universe's creation? Let's borrow an idea from a totally different field: materials science. When a crystal, like a diamond or a snowflake, forms, it grows by adding atoms into a perfect, repeating lattice. But this process is never perfect. Flaws happen. One type is called a dislocation, a break in the perfect pattern. These dislocations aren't just mistakes, they define the material's properties. A perfect crystal would be strong but brittle. It's the dislocations that let it bend without shattering. Modern electronics are built by deliberately adding imperfections, dopants, to silicon crystals. Perfection is sterile. Imperfection makes things interesting. Now, let's apply that to the cosmos. What if the Big Bang wasn't perfectly symmetrical? What if, as the universe crystallized from pure energy, a fundamental flaw, a break in the expected symmetry, was imprinted onto the fabric of spacetime itself? A primordial dislocation. In this scenario, the anomalies we see in the CMB aren't random noise. They are the stretched-out relics of a single, defining event at the dawn of time. The axis of evil and the hemispherical asymmetry would be the signature of a fundamental, preferred direction baked into the universe. The cold spot could be the scar of some violent, pre-inflationary event. These wouldn't be bugs in our model. They would be features of a new, more complex reality. A reality that wasn't born perfect, but was instead born with a beautiful, character-defining flaw. Echoes from before the beginning? To even try to explain a primordial, cosmic dislocation, we have to go beyond our standard model. We have to wander into the speculative, mind-bending world of quantum gravity, the quest to unite Einstein's theory of the very big with the quantum mechanics of the very small. And out here on the fringe, we find ideas that treat the Big Bang not as a beginning, but as a transition. One of the most exciting is loop quantum cosmology, or LQC. LQC suggests that space and time themselves aren't smooth, but are made of tiny, indivisible quantum chunks, like pixels on a screen. In standard cosmology, rewinding time leads to an infinitely dense singularity where physics breaks. LQC says, not so fast. Because space has a minimum size, it can't be crushed to nothing. Instead of a Big Bang singularity, LQC predicts a big bounce. Our expanding universe might have sprung from the collapse of a previous, contracting one. As that universe collapsed, it hit a point of maximum density, and then bounced. What we call the Big Bang was actually the moment of this cosmic rebound. This opens the door to a history before our universe. And if something came before, it could have left a mark. Research by physicists like Abhay Ashtekar and his team suggests that the violent dynamics of this pre-bounce phase could naturally explain some of the CMB anomalies, like the lack of power on large scales. A cosmic dislocation, then, could be a scar from a previous universe, an irregularity that wasn't completely smoothed out, surviving as a ghost of what came before. Another, even wilder idea comes from Nobel laureate Sir Roger Penrose. It's called conformal cyclic cosmology, or CCC. It also imagines a universe of endless cycles, or eons. But the transition is different. In Penrose's model, our universe expands until, over trillions of years, all matter is swallowed by supermassive black holes. Then, over even more unimaginable timescales, those black holes evaporate into a sea of low-energy photons via Hawking radiation. At this point, the universe is cold, dark, and empty. And here's Penrose's genius move. In a universe with no mass, there are no clocks and no rulers. Scale becomes meaningless. An infinitely large, empty universe becomes mathematically identical to an infinitely small, hot, dense one. The end of one eon seamlessly becomes the Big Bang of the next. The truly wild part is that Penrose argues evidence of the previous eon could be hiding in our CMB. He claims the final pops of evaporating black holes from the last eon would create distinct hot spots in our CMB, which he calls Hawking points. Penrose and his collaborators have published papers claiming to have found these points in the satellite data. I have to be super clear here. These claims are deeply controversial and have not been accepted by most cosmologists. Multiple independent analyses have tried and failed to reproduce the results, concluding that the so-called points are statistically impossible to tell apart from random noise. The scientific consensus is that there is no credible evidence for Hawking points. But whether LQC or CCC are right or wrong is almost beside the point. They represent a huge shift in thinking. They ask, what caused the Big Bang? They suggest our universe wasn't born from perfect nothingness, but inherited its properties, and maybe its flaws, from a past we're just beginning to imagine. Those strange patterns in the oldest light might just be the first ambiguous clues that our reality is only the latest chapter in a much, much older story. The flaw that makes reality. We've gone from a picture of cosmic perfection to the ragged edge of physics. We've seen how tiny, unexpected patterns in the Big Bang's afterglow are challenging our deepest assumptions about the universe. We've looked at explanations from simple chance, to giant voids in space, to epic theories of universes before our own. For decades, the mystery was how a perfectly smooth and symmetric early universe could create the lumpy, structured cosmos we see today. The standard answer was that random quantum fluctuations, stretched by inflation, planted the seeds for everything. The CMB anomalies don't necessarily erase that, but they add a profound, beautiful new layer. They suggest that on top of those random jitters, the universe may have been born with a coherent, large-scale asymmetry. A fundamental imperfection, a flaw. And what if that flaw isn't a problem, but the whole point? In physics, perfect symmetry is often sterile. It's the asterisk breaking of symmetry that gives rise to all the interesting stuff. The Higgs mechanism, which gives particles mass, is a form of symmetry breaking. A crystal forming from a uniform liquid is symmetry breaking. Maybe life itself is the ultimate expression of this. A perfectly uniform universe would be a thin, boring soup of hydrogen. No galaxies, no stars, no planets, no chemistry, no biology, and no consciousness to wonder about at all. The story of the cosmos, then, might not be about a perfect design. It may be the story of a perfect symmetry that was broken from the very beginning. The anomalies in the CMB could be the signature of that first, beautiful break. They could be telling us that our universe has character, a specific shape that sets it apart. We might be here not because the universe was flawless, but because it was born with just the right imperfection to allow for complexity, for structure, and ultimately, for us. This is the frontier of human knowledge. The work to figure out these anomalies is happening right now, with new telescopes and new analyses pushing the limits of what we can see. We may yet find that these flaws are just phantoms in the data. Or, we may find they're the first real glimpse into the true nature of creation. The universe isn't a flawless design, it's the result of a beautiful break in symmetry. And we are the living proof. The search for the origin of this cosmic imbalance is one of the deepest quests in all of science, and it's unfolding in real time. If you want to keep exploring these mysteries and stay on the cutting edge of cosmology, subscribe and join the journey. The biggest questions are still out there, waiting for an answer. Conclusion: from a single, perfect point to a flawed and textured canvas. The story of our universe is far stranger and more intricate than we ever imagined. The faint light from the dawn of time doesn't just show us where we came from. It hints at a reality where imperfection isn't an error, but a feature. A fundamental flaw that may have been the necessary ingredient for everything we know and are. The next generation of cosmic explorers will be the ones to figure it out. But one thing is clear. The most beautiful truths are often found in the most unexpected cracks. The cosmic glitch that created everything. For a long time, our understanding of physics suggested the universe should have been a place of perfect balance. A state where for every particle of matter, an equal and opposite particle of antimatter also existed. In this version of the cosmos, they would meet, cancel each other out, and leave behind nothing but light. The universe would be symmetrical, beautiful, and empty. But the real anomaly, however, is that we are here to observe it. Our existence is evidence of a subtle, ancient imbalance. This is a journey through that imperfection, a cosmic glitch that allowed for everything we see, and everything we are. Welcome to our exploration. If this kind of calm journey into the cosmos helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether in a quiet room or a busy city, feel free to share where you're watching or listening from. Let's explore this idea of a perfect universe. In the first moments after the Big Bang, energy converted into pairs of matter and antimatter particles. When they meet, they vanish back into energy. If this process had been perfectly symmetrical, the outcome would be inevitable. As the universe expanded and cooled, every particle would have found its partner, and the grand flare of creation would fade into an expanding void of light. There would be no building blocks for stars, for planets, or for life. It is a universe that is balanced, but also static. For change, and for complexity to emerge, that perfect symmetry had to be broken. Our existence is proof that it was. The expectation of symmetry. As a species, we seem to have a natural appreciation for symmetry. We find it in the six-fold pattern of a snowflake and the mirrored wings of a butterfly. We often build with symmetrical designs and compose music with balanced harmonies. This isn't just a cultural preference, it seems to be a fundamental part of how we perceive the world. Symmetry is often simple, predictable, and efficient. Nature itself appears to favor this approach. On a basic level, symmetry can be an efficient way to build. It requires less unique information to create a mirrored half of an organism than it does to design two distinct sides. Think of a starfish with its repeating arms, or how many animals, including us, are built on a plan of bilateral symmetry. The left side that is a near mirror of the right. This design is very effective for navigating the world with balance. The laws of physics, too, appear to be founded on deep symmetries. The principles of gravity and electromagnetism are consistent across time and space, providing a stable framework for reality. So, when physicists considered the very beginning of the universe, it was natural to assume that this principle of symmetry would hold in its most absolute form. This led them to a perplexing conclusion: the universe shouldn't contain any matter. If we journey back to that first fraction of a second, the universe was a point of incredible energy and density. Here, energy was constantly converting into pairs of matter and antimatter particles. An electron would be born with its twin, the positron. A proton with an antiproton. They share the same mass but have opposite charges, like perfect mirror images. For a brief time, the universe was a dense, chaotic soup of these pairs appearing and disappearing. A particle and its antiparticle would emerge from the background energy, and then inevitably find each other in the dense environment. Their meeting resulted in their mutual annihilation, converting their mass back into pure energy. If the universe was truly, perfectly symmetrical, then for every single particle of matter, there would have been an exact antimatter twin. As the universe expanded and cooled, this process of creation would slow, but the annihilations would continue until every particle had found its partner. The result would be a cosmos filled with light and energy, but with virtually no matter. No atoms, no gas, no stars, no planets. This is the universe that our theories of symmetry predicted. And yet, we are here. The evidence of our own existence is the clearest indication that the universe is not perfect. Somewhere, in that first moment, the symmetry was broken. An imbalance in the laws of physics. To understand the imbalance that allowed for our existence, we have to look closer at that early interaction between matter and antimatter. It seems the contest wasn't entirely fair. This subtle, universe-altering difference is known in physics as baryon asymmetry. It's the technical term for the ongoing investigation into why there is something rather than nothing. For decades, physicists have been searching for the source of this asymmetry. Our current description of the subatomic world, the standard model of particle physics, does allow for a tiny difference in how matter and antimatter behave. This is known as charge parity violation, or CP violation. Charge refers to swapping a particle with its antiparticle, and parity is like viewing its reflection in a mirror. For a long time, it was believed that the laws of physics should look the same under these combined transformations. But in 1964, an experiment studying the decay of particles called mesons revealed this wasn't always the case. The mirror, it turned out, had a crack. There was a slight, but measurable, preference for certain interactions over their mirrored, antimatter counterparts. This was the first real clue to the imbalance we see today. The problem was, the amount of CP violation observed in these particles was far too small to explain the sheer dominance of matter in the cosmos. The search continued, leading to the Large Hadron Collider at CERN. And there, the LHCb experiment, designed specifically to study these differences, provided a crucial piece of the puzzle. It has measured a CP violation in the behavior of particles called baryons. This is significant because baryons, like protons and neutrons, are the very particles that form the atomic nuclei of everything around us. The experiments showed that certain heavy baryons decay at a slightly different rate than their anti-baryon counterparts. Imagine you begin with 1 billion antimatter particles and, thanks to this slight bias, 1 billion and 1 matter particles. Now, let the annihilation begin. The 1 billion antimatter particles find their 1 billion matter partners and vanish into energy. After all the pairs have cancelled out, something is left over, that single, surviving particle of matter in a billion. It doesn't sound like much. But across the entire early universe, this 1 in a billion remainder is everything. It is every star, every galaxy, and every atom in our bodies. We are what was left over after a cosmic war that matter barely won. Our existence appears to be the consequence of a fundamental flaw in the fabric of reality. It's important to note, the amount of CP violation measured so far is still not enough to fully account for the universe we see. This tells us that our picture is incomplete, and that there are likely other sources of asymmetry yet to be discovered. A sequence of formative events. After the Great Annihilation, the universe grew quieter. It was now filled with a brilliant fog of light, and within it, a sparse mist of the surviving protons, neutrons, and electrons. The universe was no longer a featureless void of energy, it now contained substance. But a uniform cloud of particles would simply keep expanding and thinning out. For structure to emerge, another form of imperfection was needed. This came from the fabric of spacetime itself. In its first moments, the universe wasn't perfectly smooth. At the quantum level, it was a foam of tiny, random fluctuations in energy and density. Ordinarily, these fluctuations would average out to nothing. But the universe was undergoing a period of incredible expansion known as inflation. This process took those microscopic, quantum jitters and stretched them to astronomical scales. Tiny, subatomic ripples were magnified until they were light years across. The universe was now a vast, lumpy cloud of hydrogen and helium gas. There were regions that, by chance, were infinitesimally denser than others. And in the cosmos, density is destiny. Gravity began to act on these slight imperfections. A region that was slightly denser had a slightly stronger gravitational pull, and over millions of years, it began to draw in more gas. As its mass grew, its gravity grew stronger, pulling in even more matter. The denser regions became denser, and the less dense regions became the great voids of space. These tiny initial flaws became the seeds of all cosmic structure. They were the blueprint for the cosmic web, the vast network of galaxies that spans the observable universe. In the dark, vast clouds of hydrogen gas began to collapse under their own weight. As the gas compressed, the pressure and temperature at the center of the largest clouds climbed until they reached a critical threshold of about 10 million degrees. At that moment, nuclear fusion began. The immense pressure forced hydrogen nuclei to fuse together, forming helium and releasing a tremendous amount of energy. A star was born. Billions of these stars ignited, congregating in the dense regions of the cosmic web and forming the first galaxies. The universe, once dark, was now filled with light. These first stars were giants, and they lived very fast lives. When they died in massive supernova explosions, they forged heavier elements for the first time: carbon, oxygen, silicon, and iron. These stellar deaths blasted the new elements out into space, enriching the surrounding gas clouds. The next generation of stars, like our Sun, would form from this material, and swirling around them would be disks of gas and dust, rich with the raw materials for planets. This entire sequence of events, from a uniform gas to a cosmos of galaxies, was guided by those initial imperfections. Life inherits the asymmetry. This tendency towards asymmetry was passed down, from physics to chemistry, and eventually, to life itself. The glitch that shaped the cosmos also shaped us. Many of the molecules essential for life have a mirror image, a property known as chirality, from the Greek word for hand. A left-handed molecule cannot be perfectly superimposed on its right-handed twin. In a lab, chemical reactions that produce these molecules usually create a 50-50 mixture of both versions. But biology is strangely selective. The amino acids that build every protein in your body are all, without exception, left-handed. The sugar molecules that form the backbone of your DNA and RNA are all right-handed. This universal preference, called homochirality, is a defining feature of life on Earth. Why this particular choice was made is still a subject of debate. One theory suggests that meteorites seeded the early Earth with a slight surplus of left-handed amino acids. Another idea proposes that a single type of amino acid, serine, formed stable clusters that preferentially bonded with other left-handed amino acids, locking in the choice early on. This inherited asymmetry scales all the way up to the layout of our own bodies. Our heart is shifted to the left. Our liver sits mostly on the right. We are internally asymmetrical. This arrangement is determined very early in embryonic development. A tiny, swirling current of fluid, known as the nodal flow, establishes a left and right side, triggering a cascade of genes that orchestrates the asymmetric placement of our internal organs. It's a reminder that the off-center position of our heart is a direct consequence of a broken symmetry that occurred when we were barely visible. This principle appears throughout the story of evolution. The flatfish, for example, begins its life with one eye on each side of its head. As it matures, one eye migrates across its skull to sit next to the other, an adaptation for its life on the seabed. It exchanges its original symmetry for a distinct survival advantage. Similarly, the male fiddler crab develops one enormous claw, which is used not for feeding, but for defense and courtship displays. Even the human brain, while appearing symmetrical, has functions that are highly lateralized. For most people, the left hemisphere is dominant for language and logic, while the right excels at spatial and emotional processing. This division of labor allows for greater efficiency. From the first moments of creation to the workings of our own minds, the pattern is consistent. Perfect symmetry often represents a state of stillness, while an imbalance is what allows for change, complexity, and function. The one-way street. Once symmetry is broken, the path seems to be a one-way street. This idea of irreversibility is woven into both physics and biology. In physics, this is captured by the second law of thermodynamics, which states that entropy, or disorder, tends to increase. The expansion of the universe is a one-way journey. The galaxies are moving apart, and they are not expected to one day reverse course and collapse back into a single, symmetric point. The arrow of time points forward, away from that initial, simpler state. In biology, this irreversibility is set during development and reinforced by evolution. The developmental pathways that place our organs are fixed early on. A flatfish's eye does not migrate back. Evolution then acts upon these asymmetries. When an imbalance provides a survival advantage, it is strongly selected for, and the flaw becomes a defining feature. The path back to the perfect, symmetrical ancestor is effectively closed. This journey from balance to imbalance isn't a descent into chaos, it appears to be a fundamental process of creation. Conclusion: from a subtle imbalance in the first second of time, to the lopsided arrangement of the organs in our own bodies, we see the consequences of broken symmetry. It seems to be a fundamental principle that perfect balance is a state of stillness, while imperfection is what allows for motion, for structure, and for life. Our universe, and the life within it, appears to be the result of a series of these productive flaws. We are the quiet, strange, and improbable outcome of a universe that was never perfectly balanced. What examples of asymmetry in the natural world do you find most interesting? Is it the spiral of a shell, the strange form of a deep-sea creature, or something else entirely? Feel free to share your thoughts in the comments. If this kind of calm exploration into our universe helps you unwind, consider liking the video and subscribing to the channel. You won't want to miss where our journey takes us next. The flaw that built the universe. What if the most perfect thing the universe ever did was to make a mistake? From the very first moment, the cosmos was born in a state of almost impossible balance. Picture it: a searing, uniform sea of energy. The same in all directions, at every point. A world without features, without form, and without interest. It was a state of profound equilibrium, holding the potential for everything, yet containing nothing at all. And if it had stayed that way, none of this would be here. The silent dance of galaxies, the fire of a new star, the quiet complexity of a living cell. None of it would exist. The universe would be a forever empty void of light, a silent monument to its own perfection. Because the secret to our existence, the key to unlocking all the complexity and beauty we see, isn't perfection. It's a flaw, a crack in the cosmic mirror. A fundamental break written into the fabric of reality itself. This is the story of how the universe broke. And how, in breaking, it learned to build. We'll journey back to the first moments, to find the original imbalance that allowed us to be. We will watch symmetry literally shatter, revealing how order is born from chaos. We will see this same echo in the architecture of the cosmos, in the wiring of our own minds, and even in the silent logic of the worlds we are now building. By the end, you will see the world not as a pristine design, but as the beautiful, sprawling, and magnificent consequence of a single, universe-defining flaw. In the beginning, there was meant to be only light. The first moments after the Big Bang were a storm of pure energy. Here, the laws of physics were just beginning to crystallize, and a fundamental rule was taking shape. What is made can be unmade. Energy could become matter, and matter could return to energy. It wasn't just theory, it was happening constantly. Particles of light, photons, were transforming into pairs. For every particle of matter, a perfect mirror image of antimatter was born. An electron and an anti-electron. A quark and an anti-quark. They were identical in every way, except for a single opposing property. And when they met, they would vanish, their mass returning to a flash of pure light. A perfect, symmetrical cycle. The early universe was a frantic dance of creation and annihilation, a thick soup teeming with equal parts matter and antimatter. But as the universe expanded, it cooled. The light grew tired. It no longer had the energy to create new pairs. The music for the dance stopped. All that was left was the final act, a universe-wide annihilation. And here, we face a great mystery. If the balance was truly perfect, every particle should have found its anti-particle partner. The grand finale of creation would have been a cosmos entirely empty of matter. No atoms, no stars, no worlds, only a vast, fading sea of light, a ghost of the vibrant universe that could have been. But that's not what happened. We are here. Something went wrong. The symmetry wasn't perfect. In those first fractions of a second, the universe showed a slight, almost imperceptible preference. A whisper of a choice for matter over antimatter. For every billion pairs that met and vanished back into light, the universe made just one extra particle of matter. Just one in a billion. It seems like nothing, an insignificant rounding error. But that tiny crack in the foundation was everything. When the great annihilation was over, that one lonely survivor was left behind. And it wasn't just one. It was one in a billion, multiplied across the unimaginable scale of the early cosmos. This cosmic debris, this remnant of a broken symmetry, became the building blocks for everything we know. These leftovers clumped into the first protons and neutrons. Over hundreds of thousands of years, they captured electrons, forming the first atoms. And from those simple atoms, gravity, the grand architect, began its work. It pulled clouds of hydrogen and helium into vast nurseries, which collapsed to form the first stars. Inside those stellar furnaces, new elements were forged: carbon, oxygen, iron, the very material that makes up our world, and makes up us. When those stars died, they scattered these gifts across the cosmos, seeding the next generation. All of it, every galaxy, every star, every planet, every living thing, is a direct consequence of that initial, minuscule flaw. Our existence is the result of a cosmic accounting error. We are the children of a broken symmetry. The universe had to break its own rules to bring us into being. It had to choose. And in that choice, it traded the sterile perfection of an empty void for the messy, complex, and beautiful reality we inhabit. The flaw was not a bug, it was the most important feature. This idea, that structure emerges from a break in symmetry, isn't just a story from the dawn of time. It's happening all around us. To see it, we don't need to look billions of years into the past. We just need to watch something break. Imagine a perfectly smooth sheet of glass. It is a portrait of symmetry. Move across its surface, and it's the same from point to point. Now, strike it. A crack appears. For a fleeting instant, the crack is almost perfectly straight, a symmetrical line. But this state is unstable. It doesn't last. Almost immediately, the crack begins to deviate. It veers. It branches. The single, simple line shatters into a complex, hierarchical pattern, like lightning forking across the sky, or the branches of a winter tree. Why? Why doesn't it just take the most efficient path? Because the idea of a perfect material is an illusion. At the microscopic level, every material is a landscape of tiny imperfections, variations, and weak points. As the crack travels, it feels this hidden, messy terrain. A tiny weakness to the left causes it to swerve. An impurity ahead might cause it to hesitate, then split, breaking its own symmetry more dramatically. This act of breaking is not failure, it's a strategy. By branching into a complex pattern, the material finds a better way to dissipate energy. It's a way of managing a catastrophe. Nature itself has harnessed this. Consider your own bones. They are not perfect crystals. They are filled with microscopic complexities. When a bone suffers an impact, a crack doesn't shoot straight through. It is forced to navigate the disordered landscape within. It twists, turns, and branches into countless microfractures, a process that absorbs a tremendous amount of energy. The very flaws in the bone structure are what make it tough. The broken symmetry of the crack's path is what keeps the whole from shattering. We see this same principle when water freezes. As a liquid, its molecules are disordered and symmetric. Any drop looks like any other. But as it cools, the symmetry breaks. The molecules can no longer roam freely. They lock into a fixed, crystalline lattice. Ice. The random, uniform state of the liquid gives way to the ordered, patterned structure of the crystal. A new order emerges from the chaos. From the shattering of glass to the freezing of water, the lesson is the same. Perfect symmetry is a state of simplicity, of stasis. Structure, pattern, and complexity are only possible when that symmetry is broken. The universe doesn't build with perfect blueprints. It builds with the beautiful, intricate patterns that emerge from the wreckage. But is there a flaw, a break in symmetry, woven into the fabric of space itself? One that defines not just what things are made of, but the fundamental rules of their existence. Yes. And it is perhaps the most important break of all. Its architect is a field that permeates every point in the universe. It is called the Higgs field. Let's travel back again, to less than a trillionth of a second after the Big Bang. In the incredible heat of that moment, the forces of nature were unified, and all fundamental particles were essentially the same. They were all massless. Imagine a universe where every particle zips around at the speed of light. Tiny, hyperactive ghosts, unable to clump together, unable to form stable structures. A massless electron could never be captured by a massless nucleus to form an atom. A universe without mass is a universe without structure. A sterile, featureless place. So, where did mass come from? It came from a break in symmetry. As the universe expanded and cooled past a critical temperature, something happened. Imagine a ball bearing resting perfectly on the peak of a sombrero. As long as it's perfectly balanced, the situation is symmetric. This peak is the early Higgs field, in a state of high-energy symmetry. But this position is also unstable. The slightest tremor, and the ball will roll down into the circular brim. When it settles, it has found a new, lower energy state. But in doing so, it has broken the symmetry. It had to choose one specific point in the brim to rest, shattering the perfect rotational symmetry of the hat. This is what happened to the Higgs field. It underwent a phase transition, like water freezing into ice. It fell from its unstable, symmetric state into a new, lower energy state, acquiring a value everywhere throughout space. And this changed everything. Particles moving through the universe were no longer traveling through an empty void. They were moving through this newly formed Higgs field. And their interaction with this field is what we perceive as mass. Some particles, like photons, don't feel the field at all. They pass through unimpeded and remain massless. Others interact with it, as if moving through cosmic molasses. This resistance to being accelerated is their mass. The more they interact, the more massive they are. This was the moment the ghostly particles of the early cosmos acquired their substance. It was this flaw, this settling of the Higgs field into an imperfect state, that allowed for the rich diversity of particles we see today. And with mass, gravity could finally take hold. Before, particles were flying apart too quickly. Now, massive particles could be corralled. Tiny quantum ripples from the dawn of time now had something to work with. Regions that were infinitesimally denser began to pull matter in. Over millions of years, these seeds of structure grew into the vast filaments of the cosmic web, the great walls of galaxies, the clusters and superclusters, the stars, the planets, and eventually, us. The grand architecture of the cosmos is a fossilized record of two fundamental flaws: the tiny quantum ripples that broke the universe's initial smoothness, and the breaking of the Higgs symmetry, which gave those ripples the mass they needed to grow. Without that spontaneous fall from grace, the universe would have remained a thin, featureless soup of light-speed particles. Forever symmetrical, and forever empty. Once you start looking for it, you see this blueprint everywhere. The principle that order arises from a break in symmetry repeats itself at every scale of existence. Journey from the cosmic to the biological. Look at the veins on a leaf, or the neural network inside your brain. They follow a beautiful, branching pattern. A large artery splits into smaller ones, which split into smaller ones still. There is a kind of symmetry to it. The pattern looks roughly the same at different scales. But this growth doesn't continue into chaos. It's tamed. The perfect, infinite fractal symmetry is broken by the practical requirements of a living thing. The need to supply a specific volume of tissue provides a boundary. The physical limits of cell walls introduce a preferred scale, a point where the branching must stop and organize. It is this break that turns a chaotic pattern into a functional network. The structure of your heart, your lungs, your brain, they are all masterpieces born from attained, broken symmetry. Now, let's take a leap into the worlds we are creating ourselves. Artificial intelligence. When we build a neural network, we start with a kind of perfect symmetry. The connections between its neurons are set to small, random values. It's a blank slate, full of potential, but knowing nothing. To make it learn, we show it the world. With each attempt to understand, it adjusts its connections. This learning process is a massive act of symmetry breaking. As the network learns, certain connections grow stronger, while others wither away to nothing. It discovers that not all connections are equal. It develops hierarchies. Some neurons become specialists for simple things, like lines or colors. Others learn to combine these into more complex ideas, like eyes or faces. This mirrors what we see in nature. The initial, symmetric state is like the early universe. The training process is the cooling that forces the symmetry to break. The result, a sparse, hierarchical, and highly specialized structure, is the complex order that emerges. The network discovers for itself that a flawed, incomplete, and broken structure is far more powerful than a perfect, fully connected one. From the shape of galaxies to the neurons in your head, to the logic of the ice we are building to emulate our own minds, the same story unfolds. A state of perfect symmetry is a state of stasis. It is the breaking of that symmetry that introduces the differences, the hierarchies, and the relationships that allow for genuine complexity and function. We have journeyed through the flaws in matter, in structure, and in thought. But there is one final, all-encompassing asymmetry that governs our entire experience. It is so fundamental, we barely notice it. It is the flaw that gives the universe a story. It is the arrow of time. Why does time only move forward? Why do we remember the past, but not the future? Why does a glass shatter, but we never see the shards leap back together? This might seem like a simple question, but it is one of the deepest mysteries in physics. At the most microscopic level, the fundamental laws of nature don't have a preferred direction of time. A video of two particles colliding looks just as valid played forwards or backwards. And yet, in our world, the direction of time is undeniable. This break in temporal symmetry is what allows for everything we call a process. It allows for cause and effect. It allows for life and for death. Without the arrow of time, the universe would be a static block of spacetime where nothing ever truly happens. So where does this colossal asymmetry come from? It comes from a special, flawed, condition at the very beginning. The universe was born in a state of profound and unnatural order. The energy and matter were distributed with an incredible smoothness, a very low entropy configuration. It's like finding a perfectly wound-up clock. The mystery isn't that the clock is unwinding. The mystery is who wound it up. This initial, highly ordered state is the ultimate broken symmetry of our cosmos. The primordial flaw that set the entire story in motion. The arrow of time is simply the direction of that unwinding. We experience time moving forward because we are living in a universe that is progressing from order to disorder. The sun shines because it is converting its highly ordered fuel into disordered light and heat. Life itself is a magnificent, local rebellion against this tide. An organism maintains its incredible internal order by taking in ordered energy from its environment and expelling disordered waste. We are complex islands of order, temporarily staving off the inevitable march towards chaos. Our memories are records of past states that were more ordered than the present. The very act of thinking generates entropy in our brains. The arrow of time is not something that happens to the universe. It is the unfolding of the universe, driven by the asymmetry between its highly ordered beginning and its disordered future. The fact that we have a past, a present, and a future is a gift from this one great temporal flaw. We began with a question: what if perfection was a mistake? The answer has echoed back from every corner of the cosmos. We learned that if the universe had been born perfectly symmetrical, it would have remained perfectly empty. Our very substance is the remnant of a 1 in a billion flaw between matter and antimatter. We saw how the illusion of perfection shatters, literally, and how a simple crack can weave a complex, resilient structure. Order is not the absence of chaos, but a pattern born from it. We found the Higgs field, whose fall from a perfect state gave mass and substance to a ghostly universe, allowing gravity to sculpt the worlds we see today. We saw this blueprint repeated in the branching of our own veins and the firing of our own neurons, discovering that breaking symmetry is the only way to build meaning. And finally, we confronted the most profound asymmetry of all: the arrow of time, the grand, unfolding narrative of the cosmos, made possible only by the universe's flawed beginning in a state of impossible order. The story of the universe is the story of broken symmetry. It tells us that perfection is sterile, that balance is stasis, that it is in the cracks, the imbalances, and the flaws that true creativity lies. The world is not evidence of a flawless design, but of a dynamic, imperfect process of becoming. We are not an exception to this rule. We are its ultimate expression. We are the chaotic, complex, and improbable result of a series of fortunate flaws. Our existence is a testament to the fact that the universe did not need to be perfect to be beautiful. It just needed to be broken. If this journey into the flaws that shape our reality sparked something in you, consider joining us for more explorations into the great questions of the cosmos. The day the universe shattered forever. Before there were stars, before there was even a direction to travel in, the universe was simple. It was a single, quiet state. A place where every particle was a mirror of another, and all the rules were woven into one. Imagine an ocean of pure energy, perfectly smooth, without a single ripple. This was reality in its first form. But simplicity, it turns out, is sterile. In that flawless cosmos, nothing could form. No galaxies, no planets, no us. For the complex, strange, and beautiful universe we know to exist, that primordial quiet had to be broken. What if the universe had to give up its own perfection just for you to exist? This is the story of that moment. A change so deep it didn't happen in a place, but created places. A moment the universe traded its eternal calm for the beautiful, unpredictable world we call home. The quiet beginning. To understand the change, we have to imagine what was there before. We need to go back to a time so early it dissolves in our hands. To the first trillionth of a second. Here, the universe was almost unimaginably hot. It wasn't a place of things, but a soup of pure energy and fundamental particles. But this soup had a profound and beautiful property: symmetry. When we think of symmetry, we might picture a snowflake. But in physics, it's a deeper idea. A law has symmetry if it stays the same when you change something, like your location. Gravity works the same here as it does on the other side of the planet. It has a symmetry of place. The great physicist Emmy Noether showed that these symmetries are where the laws of conservation come from, the rules that say energy or momentum can't just disappear. Symmetry isn't just about looks, it's the source of order. In the very early universe, the symmetries were extreme. The universe itself was the same in every direction and at every point. But more than that, the fundamental forces of nature, so different to us now, were a single, unified force. Today we know four forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. But in the heat of that first moment, the electromagnetic force and the weak force were one and the same, a single, electroweak, force. A particle of light was indistinguishable from the particles that now govern radioactive decay. They were all part of the same family. And it wasn't just the forces. Every particle was massless. Electrons, quarks, all of them were like ghosts. They flew at the speed of light, unable to slow down, unable to bind together, unable to form anything. A universe of massless particles is a universe where nothing can ever truly hold on. It's a reality of pure energy, where particles dance but never become. This was the state of simple perfection. A universe with a more unified set of rules than we see today. But it was also a universe with no shape, no clumps of matter, just a uniform, radiant fog. It was beautiful, simple, and complete. And it had to end. The cosmic cooling. The simple, early universe carried the seeds of its own transformation. From its very first moment, the story of the cosmos has been one of expansion and cooling. As space stretches, the energy within it spreads out, and the temperature drops. This cooling was the quiet pressure for change. That perfect symmetry, it turns out, was only stable at incredibly high temperatures. Think of it like water vapor or steam. At high temperatures, water molecules fly about randomly. The steam looks the same in every direction, it's symmetrical. But as you cool it, it condenses into liquid. Cool it further, to freezing, and something dramatic happens. The water molecules begin to lock into a fixed, crystalline lattice. They form ice. An ice crystal isn't perfectly symmetrical like the steam was. It has specific axes, preferred directions. The random, uniform state of water has spontaneously chosen a specific orientation as it froze. The first, simple symmetry has been broken. The early universe was facing a similar kind of freezing point. As it expanded and cooled, the unified electroweak state was becoming unstable. The universe was approaching a critical temperature, a precipice. Above this temperature, symmetry was the natural state. Below it, the universe would have to choose. It would have to fall into a new, lower energy state, one that didn't have the same simple symmetry. A mere picosecond, 1/1,000,000th of a second, was about to pass. In our terms, an impossibly short time. But for the young universe, it was long enough for the expansion to cool it to the very edge of this change. The ocean of calm was about to freeze, and in doing so, it would shatter the principles of its own existence. The change. And then, it happened. Around 1/1,000,000th of a second after the Big Bang, the universe crossed the threshold. The temperature dropped, and the elegant symmetry of the electroweak era was broken. Spontaneously. Irreversibly. This event is known as spontaneous symmetry breaking. It wasn't an explosion. It was more like a phase transition of space itself. The very fabric of reality reconfigured. The agent of this change is something we now call the Higgs field. The Higgs field is a field of energy that permeates every point in spacetime. Before the change, at high temperatures, the field had a value of 0 everywhere. It was off. In this state, it didn't affect other particles, and the world was symmetrical. Physicists visualize this with an analogy: a Mexican hat potential. Imagine a sombrero with a high peak in the middle and a round, circular trough. The height on the hat represents an energy level. In the hot, early universe, the Higgs field was like a ball balanced on the very tip of the hat's peak. This is a point of high energy, but it's symmetrical. Every direction down into the brim is the same. But this position is also unstable. The slightest nudge will make the ball roll down into the lower energy state of the brim. As the universe cooled, the energy needed to keep the ball balanced on the peak was no longer there. The system had to fall. It had to settle into its true ground state, its lowest possible energy. And so, the ball rolled. The Higgs field tumbled from its zero-value state at the peak, down into the trough of the hat's brim. This was the spontaneous breaking of symmetry. Once the ball is in the brim, it is no longer in a symmetric position. It has picked a random point in that circular trough to settle in. While the hat itself, the underlying law, is still symmetrical, the state of the system is not. The symmetry is now hidden. When the Higgs field fell into this lower energy state, its value across the universe changed from zero to something new. It switched on, and this had immediate and profound consequences. It was as if the rules of the game had quietly been rewritten. This wasn't a gentle slide. It was like supercooled water instantly snapping into ice. Space itself froze into a new configuration. Before, particles moved freely. Now, the medium itself had become sticky for some of them. The tranquil ocean had become a kind of thick molasses, but a strange molasses that only some things could feel. The universe did not just cool, it fundamentally transformed. The simplicity was gone, replaced by a new, lopsided, and far more interesting reality. A universe reborn. This breaking was not an act of destruction. It was an act of creation. The consequences of the Higgs field settling into its new state rippled through the cosmos, giving birth to the universe we recognize. New forms of being became possible. First consequence: the origin of mass. The first and most famous consequence was that particles acquired mass. Before, everything was massless, moving at the speed of light. A universe without mass is a universe without structure. Mass allows particles to slow down, to be caught, to gather. Without it, there are no atoms, no planets, no stars. When the Higgs field switched on, it was as if a kind of cosmic drag appeared. Particles that interacted with this new field found it harder to move through space. Think of it like walking through a quiet field, and then the field is suddenly filled with tall grass. Your movement is resisted. This resistance to a change in motion is what we call mass. A photon doesn't interact with the Higgs field, so it feels no resistance. It continues on at the speed of light, like a path with no grass. An electron interacts a little, so it gains a little mass. A top quark interacts very strongly, and becomes very heavy. For the first time, there was a hierarchy. Not all particles were the same anymore. This was the first step toward complexity. It allowed the frantic dance of the early universe to slow down. Matter could now begin to take hold. Second consequence: the parting of the forces. The second great consequence was the separation of the electroweak force. In the age of simplicity, the electromagnetic force and the weak nuclear force were one. The breaking of symmetry pulled them apart. One of the four force-carrying particles, the photon, did not interact with the Higgs field. It remained massless, and became the carrier of a new, distinct force: electromagnetism. Because it's massless, its range is infinite. This is the force that would one day hold atoms together and carry the light that lets us see. The other three carriers, the W and Z bosons, did interact strongly with the Higgs field. They became incredibly massive. According to quantum mechanics, a massive force carrier means a short-ranged force. This new, short-ranged force was the weak nuclear force. It became so feeble and limited that it only works inside an atomic nucleus. It may seem minor, but it's the weak force that drives the nuclear reactions in our sun and allows for the radioactive decay that helps create a diversity of elements. So from one interaction, two very different forces were born. One long-range and familiar, governing the world of structures. The other short-range and hidden, quietly working inside stars and atoms. Third consequence: the seeds of places. Perfection is smooth. Creation needs texture. If the early universe had been perfectly uniform, it would have stayed that way. As it expanded, it would have become a thinner and thinner gas. Gravity would have had nothing to grab onto. The beautiful chaos of our universe, the galaxies, the stars, all began as tiny imperfections. These came from quantum fluctuations, tiny, fleeting variations in energy that flicker in and out of existence in the vacuum of space. During a period of hyper-fast expansion called inflation, these microscopic ripples were stretched to astronomical scales. When electroweak symmetry breaking happened, it froze these density differences in. The new property of mass gave these tiny, denser regions a little more gravitational pull. Over hundreds of millions of years, that tiny advantage was all that was needed. The slightly denser regions slowly pulled in matter from the regions around them. What began as a nearly invisible imperfection grew into a cloud of gas. That cloud grew into a proto-galaxy. And inside those, smaller knots collapsed to form the first stars. The breaking of symmetry allowed the first real places to grow. Our existence is written in the tiny imperfections of that once smooth state. Fourth consequence: the flow of time. Perhaps the most philosophical consequence is the direction of time itself. At the deepest level, the laws of physics seem to work the same forwards and backwards. But our world clearly has a one-way street for time. Things break, but they don't unbreak. This is the second law of thermodynamics. The idea that disorder, or entropy, tends to increase. The early universe, in its simple, uniform state, was actually a state of very low entropy. It was orderly and predictable. The act of symmetry breaking, of falling from a single, simple state into one of many possible complex ones, was a massive, universe-spanning increase in entropy. It was a move from simplicity to complexity. By breaking its symmetry, the universe traded its timeless perfection for an irreversible, forward-moving history. The event created a profound difference between the past, the symmetric state, and the future, the broken state. It set the cosmic clock in motion. The quiet, eternal now of the early cosmos was traded for a universe that has a story. Our place in the aftermath. And so, here we are. Billions of years later, on a small planet, the descendants of that ancient change. The breaking of symmetry isn't a distant event. It's why we are here. The very atoms in our bodies are a testament to this broken simplicity. The quarks that build our protons and neutrons have mass because of the Higgs field. Our atoms are held together by the electromagnetic force, which was born from that split. The heavy elements that make life possible, carbon, oxygen, iron, were forged in stars. And those stars could only form because the breaking of symmetry allowed matter to clump together and ignite. Our existence is built on a series of cosmic imperfections. The universe traded its eternal, simple quiet for the possibility of structure, chemistry, and eventually, life. It was a trade of calm for consciousness. And yet, whispers of that lost simplicity remain. The conservation laws that anchor our reality are the echoes of those original symmetries. Even in the chaos, there is an underlying order. This search for deeper patterns is, in a way, a search for our most ancient cosmic heritage. Conclusion: the story of the universe is a story of transformations. Of simple states breaking to allow for more complex ones. Exploring these moments helps us understand where everything came from, and what our place in it is. If you want to continue these journeys with us, subscribe to the channel for more explorations into our strange and beautiful cosmos. The next time you look up at the night sky, at the scattered and beautiful tapestry of stars, take a moment. Remember the price that was paid for that view. Remember the simple, silent, and featureless universe that had to change so that this, and you, could come to be. You are not just looking at the stars. You're looking at the magnificent, glittering aftermath of a broken perfection. The final day of perfect symmetry. What if the story of our existence wasn't a moment of pure creation, but a moment of breaking? What if the reason there is something, rather than a uniform nothing, is because the universe, in its earliest moments, changed its state? Imagine a condition of absolute perfection. A flawless, featureless state where every particle is identical and every force is one. It sounds orderly, perhaps even beautiful. But this state was also one without complexity, without structure, and without time as we know it. For anything to happen, for the story of the cosmos to begin, that perfection had to give way to something else. This is a journey into the final moments of that perfect symmetry. A quiet, yet profound transition that, once it occurred, was irreversible, unleashing the arrow of time and all of complexity. It was the point of no return, a fundamental change that made everything you see, and everything you are, possible. Before the Big Bang as a hot, dense state, and before time itself had a clear direction, there was a condition we can only approach with theory. Physicists refer to it as the Planck epoch. It lasted for a fraction of a second, so small it is difficult to comprehend, just 10 to the minus 43 seconds. During this instant, it is hypothesized that the four fundamental forces of nature we know, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single primordial force. The universe was in a state of profound and elegant symmetry. It was a place where, in a sense, nothing could truly happen because everything was already the same. There were no distinct particles or structures. But perfect symmetry, as it turns out, can be an unstable condition. Think of a pencil balanced perfectly on its sharpest point. The slightest tremor is enough to make it fall. But in a perfectly symmetrical system, there is no preferred direction for it to fall. And yet, it must fall. The early universe was like that pencil. And in a moment of immense consequence, it fell. That fall, that breaking of symmetry, is one of the most important events in the history of the cosmos. Without it, there would be no matter as we know it, no stars, no planets, and no us. The story of our universe is the story of this broken perfection. The world of perfect symmetry. To understand what was lost in that transition, we first need to build a picture of this state. What does a universe of perfect symmetry look like? In physics, symmetry is not just about visual similarity, like in a snowflake. A system has symmetry if you can change it in some way, and its fundamental properties remain the same. The laws of physics, for instance, are the same here as they are on the other side of the galaxy. That's a symmetry in space. In the earliest moments of the universe, these symmetries were far more profound. At extreme energies, the fundamental forces of nature were likely indistinguishable from one another. This is the core idea of grand unification theories, or GUTs, which propose that the electromagnetic, weak, and strong forces were all facets of a single, unified, electronuclear force. Imagine a perfectly still, frozen lake. From above, it looks completely uniform. This is like the early universe. The forces were unified, just as water molecules are locked together in a uniform crystal. In this state, particles like quarks and electrons were essentially massless, moving at the speed of light. Without mass, particles could not clump together to form atoms, let alone stars or galaxies. The universe was a featureless, uniform soup of energy. Physicists describe this state using a concept called a scalar field, a value that exists at every point in space. In the symmetrical universe, this field was at a point of high energy but perfect balance, like a ball resting on the peak of a perfectly shaped hill. As long as the ball remains centered, the symmetry is maintained. This was the universe on the eve of its great transformation, a realm of flawless but empty potential. The temperature was so high that the distinction between forces hadn't yet frozen out. For the cosmos to become interesting, to develop structure and complexity, this symmetrical state had to end. The ball had to roll off the hill. And as the universe began its expansion and cooling, that is what happened. The final day of perfect symmetry was ending, and with it, the birth of everything we know was beginning. The shattering, electroweak symmetry breaking. The end of perfect symmetry was not a single event, but a series of transitions. As the universe expanded, it cooled. And with cooling come phase transitions, the same phenomenon that turns steam into water and water into ice. In these cosmic phase transitions, the fundamental nature of reality changed. While gravity may have separated from the other forces at the very beginning, one of the most well understood of these events is known as electroweak symmetry breaking. This was a moment when the universe we know truly began to take shape. It happened when the universe was about a trillionth of a second old, and the temperature had dropped to around 10 to the 15 degrees Kelvin. Above this temperature, the electromagnetic force and the weak nuclear force were unified into a single, electroweak, interaction. As the universe cooled past this critical point, the electroweak symmetry spontaneously broke. Here, the analogy of the ball on the hill becomes useful. The hill represents a concept called the Higgs potential. At high temperatures, the potential has a single minimum at the center, representing the symmetric state. But as the temperature drops, the shape of this potential changes. The center becomes an unstable peak, and a lower energy trough forms around it, like the brim of a hat. The universe, always seeking a lower energy state, had to change. The Higgs field, which had been at zero, had to roll down into this new trough. But the trough is a continuous circle of points with the same low energy. The field had to fall into one of these points at random. The moment it settled, the symmetry was broken. A specific value in an abstract space was chosen, and this choice rippled through the cosmos. This process is called spontaneous symmetry breaking. The underlying laws of physics remain symmetric, but the ground state of the universe, the state it settled into, is not. The consequences were immediate. The single electroweak force split into two, the familiar electromagnetic force and the weak nuclear force. The force-carrying particles also changed. Of the four massless carriers of the electroweak force, one remained massless, the photon. The other three, the W and Z bosons, acquired mass through their interaction with this newly settled Higgs field. This is why the weak force became short-ranged, while the electromagnetic force remained infinite in range. This was also the moment that mass itself came into being for many fundamental particles. Particles like quarks and electrons, which had been massless, began to interact with the Higgs field. You can think of this field as a medium now filling all of space. Some particles, like photons, do not interact with it and continue at the speed of light. Others, like the top quark and W and Z bosons, interact with it strongly and become very heavy. The perfect simplicity was gone, replaced by a more complex, but far more interesting, reality. This set the stage for atoms to form and for gravity to pull matter together. The final day of perfect symmetry was over, and in its place, the universe of substance and structure was born. A cascade of consequences, an arrow of time and a lumpy universe. The breaking of symmetry was not an end, but a beginning. It triggered a cascade of consequences that sculpted the universe and gave it a direction. Before this, in the state of perfect equilibrium, time itself had little meaning. But the fall from a high-energy, symmetric state to a lower-energy, broken symmetry state was an irreversible act. This is where the concept of the arrow of time enters the cosmic story. This irreversibility is tied to the second law of thermodynamics, which states that the entropy, or disorder, of a closed system tends to increase. The initial, perfectly symmetric state was one of very low entropy, it was highly ordered. The breaking of that symmetry was like dropping an unbroken egg. The universe transitioned from a simple, low-entropy state to a more complex, higher-entropy one. This spontaneous change is a key component of what gives time its forward direction. The universe could not go back to its perfectly symmetric state, any more than a shattered egg can reassemble itself. But the breaking of symmetry also helped make the universe lumpy. In the moments during these transitions, the universe wasn't perfectly smooth. It was subject to the randomness of the quantum world. Tiny quantum fluctuations, random jitters in the energy of empty space, are believed to have been magnified to cosmic scales during a period of hyper-expansion known as cosmic inflation. These fluctuations were the seeds of all structure. Imagine a perfectly smooth, flat sheet. Inflation stretched this sheet to an astronomical size. But if there were tiny, microscopic wrinkles in the sheet, those wrinkles would be stretched out too, becoming vast, but very slight, variations in density. This is what seems to have happened to the universe. After symmetry breaking gave particles mass, these tiny density variations became very important. Gravity, now able to act on massive particles, began to pull matter toward the slightly denser regions. Over millions and then billions of years, this process continued. Dense regions became denser, pulling in more matter, while less dense regions became emptier, forming vast cosmic voids. This is the origin of the cosmic web, the filamentary structure of galaxy clusters and superclusters that spans the observable universe. Those tiny quantum jitters, amplified by inflation and then acted upon by gravity after symmetry was broken, are the reason we have galaxies, stars, and planets. Without the breaking of symmetry, there would be no mass for gravity to work with. Without the tiny imperfections from quantum fluctuations, there would be no seeds for structures to grow from. The universe might have remained a thin, uniform soup of particles. Our existence can be traced back to this primordial imperfection. The legacy of imperfection, the final day of perfect symmetry was, in a way, the first day of our kind of universe. Every aspect of our reality is a legacy of that primordial shattering. This imperfection is not a flaw, it appears to be the engine of complexity. Consider the four fundamental forces. The fact that they are different is a direct result of symmetry breaking. Gravity sculpts the large-scale structure of the cosmos. The electromagnetic force allows atoms to bind into molecules, creating the diversity of matter we see. The two nuclear forces operate on the subatomic scale. The strong force binds atomic nuclei together, creating stable elements. The weak force, which emerged from the electroweak symmetry breaking with its massive carriers, governs radioactive decay, a process crucial for the energy production in stars like our Sun. If electroweak symmetry had never broken, atoms as we know them could not form. There would be no chemistry, no stable structures, and likely no life. Furthermore, the asymmetry between matter and antimatter, the fact that the universe is made almost entirely of matter, is thought to be another consequence of broken symmetries in the early universe. Had they been perfectly balanced, matter and antimatter would have annihilated each other, leaving behind only radiation. The fact that a small surplus of matter remained suggests a fundamental symmetry was violated. That tiny remnant was all that was left to form the galaxies, stars, and us. From the largest cosmic structures to the smallest subatomic interactions, our universe is defined by its broken symmetries. The elegant, perfect state of the beginning was sacrificed for the complex, lumpy, and creative universe we inhabit. So, we return to the quiet question of our cosmic origins. What if the secret to our existence was not simply an act of creation, but a series of symmetry-breaking events? This idea lies at the heart of our modern understanding of the cosmos. We began in a state of theorized perfect symmetry, where all forces were one and key particles were massless. This pristine state was unstable. As the universe expanded and cooled, it underwent phase transitions. The breaking of the electroweak symmetry gave mass to fundamental particles, established the distinct identities of the forces, and helped set in motion an irreversible trend from order to disorder, contributing to the forward arrow of time. The final day of perfect symmetry was not an end. It was the necessary transition that allowed the universe to become interesting. It was the moment that potential became reality. The breaking of that initial, perfect balance was the generative act of the cosmos. Every star, every planet, every thought, is a distant echo of that primordial shattering. We are the legacy of an imperfect universe. Our existence is proof that from a broken symmetry, a profound and beautiful complexity can emerge. And in a quiet, cosmic irony, it is this consciousness, born from imperfection, that now looks back across 13.8 billion years, piecing together the story of how that perfect symmetry was lost, and in that loss, how everything was gained. The final day of perfect symmetry was not the end of the story. It was page 1, why everything is secretly unfair. There is a story we are told, and it is a simple one. It's a quiet, comforting story about balance, about equilibrium. We see it in the world around us, or we think we do. A world built on the clean principle of a perfectly weighted scale. For every rise, a fall. For every action, an equal and opposite reaction. We are shown that our markets are a balanced game of supply and demand, that our digital spaces are open places for ideas. It's a beautiful idea, symmetrical, orderly, but sometimes the most beautiful ideas are the ones that hide the most. What if the symmetry we see is just a trick of the light? A quiet illusion designed to hide a deep and growing imbalance. Imagine a staircase. It seems to climb steadily upward. But if you shift your perspective, just for a moment, the staircase reverses. It now appears to descend. Nothing has changed in the staircase itself, only in how you are seeing it. That feeling, that subtle, internal shift where what seemed certain is suddenly not, that is the state of our modern world. We believe we are on a staircase leading up, while unseen forces may be changing its direction beneath our feet. This is a journey through those hidden imbalances. By the end, you may start to see the world a little differently. You may start to see the tilt in the scale, the subtle illusions that shape our reality. If this kind of calm exploration helps you think, consider liking the video and subscribing. And wherever you are right now, feel free to share where you're watching or listening from. The quiet lie of symmetry. The story begins in a very fundamental place, our own minds. Our brains seem to have a preference for patterns, for order, and especially for symmetry. It's a kind of evolutionary shorthand. A symmetrical shape can feel safe, predictable. We are drawn to it, we trust it, and because of this, we can be quietly fooled. Consider one of the simplest visual tricks, the vertical-horizontal illusion. If you are shown a perfect square, your brain may tell you that it's not a square at all. It might appear as a rectangle, just slightly taller than it is wide. This is because our visual system has a quiet bias. It tends to exaggerate vertical lines. This isn't just a curious party trick. It's a subtle distortion embedded in the world we've built. Designers know this. When they create a button on a screen that they want you to perceive as perfectly square, they sometimes have to make it geometrically imperfect. The balance you feel on the screen isn't always real. It's often a careful compensation for the imbalance in your own perception. It gets deeper. Let's talk about the shadows that aren't there. The Mach band's illusion shows this well. When you place two shades of gray next to each other, your brain quietly generates a thin, dark line on the darker side of the boundary, and a thin, bright line on the lighter side. These bands don't exist in the image. They are phantoms created by our visual cortex, an attempt to enhance the contrast and make the edge clearer. Our brain is actively editing reality for what it thinks is our own good. This means that a very gentle gradient can be made to feel like a sharp cliff. This is the principle behind the cornsweet illusion. An image is divided by a central line and shaded with a faint gradient. The two halves of the image are, in fact, the exact same color. But because of that gradient and the dividing line, your brain becomes convinced that one side is much darker than the other. When the line is removed, the illusion dissolves. The symmetry was there all along, but it was hidden by a subtle manipulation of context. This serves as a quiet metaphor for our economic and social systems. A single line, a single rule, can make two identical situations feel fundamentally different. These are not just curiosities. Architects have used these principles for centuries. An Ames room is a remarkable piece of this kind of design. From the outside, it is a distorted, trapezoidal chamber. But when you look through a specific peephole, it appears to be a perfectly normal, cubic room. The effect is strange. A person walking from one corner to another will seem to grow or shrink dramatically. The illusion is so strong it overrides our rational mind. We see the impossible happen because we trust the false symmetry of the room's appearance. We assume the walls are parallel and the floor is level. So when we are placed inside a system that is secretly tilted, we don't question the system. We question what we are seeing. We believe a person has shrunk, rather than believing the room itself is a lie. This is the foundational idea. The world can sometimes present itself as an Ames room. It gives us a peephole, a curated view of fair markets and equal opportunity. And through this peephole, everything can look symmetrical. So when we see strange outcomes, one person working a lifetime with little to show for it, while another gains great wealth for doing very little, we don't always blame the tilted room. We create stories to make it make sense. We tell ourselves the person who shrank must not have worked hard enough. We rationalize the distortion because it is difficult to believe that the room itself, the system we are in, might be built on an incline. There's another effect, the flashed face distortion effect, that shows how our brains can create monsters out of the mundane. If you stare at a central point while a rapid series of faces is flashed in your peripheral vision, those faces begin to warp into strange caricatures. Eyes grow large, jaws stretch. These are normal faces. But the combination of low-resolution peripheral vision and rapid presentation overloads the brain's facial recognition system. In its effort to keep up, it exaggerates features, creating images that aren't there. Now, think of our information environment. We are surrounded by a high-speed stream of headlines and notifications, often viewed from the periphery of our attention. Is it surprising, then, that we begin to see distortions? That entire groups of people, viewed through this rapid, low-resolution feed, can begin to look like monstrous caricatures? The system is not always designed for nuanced understanding. It is often designed for overload. And in that overload, the complex symmetry of human society can be warped. The fairness we assume can be a cognitive illusion, a story we tell ourselves because the alternative is difficult to confront. The unseen shape of the marketplace. The journey from visual illusion to economic reality is not a leap. It is a change in focus. The same principles of hidden information and engineered perception that trick our eyes also appear in the worlds of commerce and finance. The perfectly symmetrical chart of supply and demand, where prices settle at a fair point, is perhaps the biggest optical illusion of all. This is the world of information asymmetry, the term for when one party in a transaction knows more than the other. It is a quiet engine of unfairness. The classic illustration of this comes from George Akerlof's Nobel Prize-winning idea, the market for lemons. Imagine the world of used cars. On the surface, it seems balanced. There are buyers and sellers. But there is a hidden imbalance. The seller knows the true condition of the car. The strange noise on cold mornings, the rust painted over. The buyer knows very little. So, what does a rational buyer do? Unable to tell a good car, a peach, from a bad one, a lemon, they are only willing to pay an average price that accounts for that risk. But here is where the system begins to shift. If you own a genuine peach, you know your car is worth more than that low, average price. So, you pull your high-quality car off the market. This changes the mix of cars left for sale. The proportion of lemons to peaches goes up. The average quality of cars on the market goes down. Buyers notice this over time and lower the average price they're willing to pay again. This, in turn, causes the owners of the remaining good cars to pull their cars off the market. It is a quiet, downward spiral of quality, until mostly lemons remain. The market for good used cars doesn't just shrink, it can fade away, a market failure driven purely by an imbalance of information. This is not just about used cars. It's about health insurance. You know more about your health than the insurance company. If a company offers one average price, the people most likely to sign up are those who expect to need a lot of care. Healthy people might decide the premium isn't worth it. As they drop out, the pool of insured people becomes riskier, forcing premiums to rise, which drives out even more healthy people. This is the adverse selection death spiral. It looks like a fair system, but the hidden asymmetry of information makes it inherently unstable. Now, let's look at the stock market. We are told a story of democratization, that anyone can be an investor. The ticker tape streams by, a dance of green and red. For every buyer, a seller. Perfect symmetry. But the information is not symmetrical. Consider the executives inside a company. They have inside information. They know long before the public if a new product is facing delays or a partnership is failing. While trading on most of this is illegal, the lines can be blurry. They can subtly stop buying stock or change their compensation plans based on knowledge the public does not have. Consider corporate stock buybacks. A company uses its profits to buy its own shares, which usually makes the stock price go up. This is presented as returning value to shareholders. But the executives who make this decision often have their bonuses tied to that same stock price. They have the ultimate inside information. They know when the company will be buying its own stock, creating artificial demand. The average investor is simply reacting to public news, while insiders are playing a game where they control one of the largest players. It's like a game where one person can see a card that others cannot. You might win a hand, but the house has a structural advantage. Financial markets are filled with these quiet imbalances. Sophisticated investors are given access to opportunities legally barred from the retail investor, justified as a form of protection. The very language can be obscure. The whole system presents a facade of balance, while operating on a hidden level of privilege and unequal knowledge. It is an Ames room, and from the peephole, everyone seems to have an equal chance. But on the inside, the floor is tilted. The game is imbalanced not always because people are cheating, but because the rules themselves were written to favor the person who has the blueprint of the room. The illusion of choice in the digital world. If the 20th century was shaped by information asymmetry in physical markets, the 21st is being shaped by an even more personal imbalance in the digital realm. We have moved from the market for lemons to the market for you. The illusion here is grander. It is the illusion of the open platform, the digital town square where every voice is equal. Let's begin with the window through which many of us see the world, Google. With a market share of over 90% in many places, it is not a search engine, it is the search engine. This dominance is not simply a product of merit. Antitrust cases have revealed the billions of dollars Google pays companies like Apple to be the default search engine on their devices. The choice we think we have is, in many cases, a predetermined outcome. The result is a quiet concentration of power. The results on the first page of a search receive the vast majority of clicks. By controlling that ranking, Google is, in effect, editing reality for billions of people. We are asked to trust that the algorithm is a neutral arbiter of truth. But it's a machine built by a corporation with its own interests. This creates a new kind of power. When Canada attempted to implement a digital services tax, the United States government threatened retaliatory tariffs to protect its tech giants, pressuring Canada to adjust its approach. During the conflict in Ukraine, it was reported that the head of Starlink, Elon Musk, denied a request to extend satellite coverage for a drone attack, a unilateral decision with major battlefield consequences. When a private company controls essential infrastructure, the line between CEO and head of state can begin to blur. This asymmetry is mirrored on the platforms we use to connect. Meta's empire, Facebook, Instagram, WhatsApp, is used by nearly half the world's population. We see them as separate tools, but they are part of a single data gathering apparatus. The illusion is community. The reality is a form of behavioral analysis on a vast scale. They know our friends, our fears, our political leanings. We, in return, know almost nothing about how they use this data. This creates the conditions for algorithmic price discrimination. If you search for a flight and come back an hour later to a higher price, the algorithm may have noted your interest. It can show different prices to different people based on their browsing history or location. This is a personalized penalty for showing intent. But the deeper asymmetry is in the feed itself. It feels like a random stream of updates, but it is a highly engineered system. The algorithm's primary goal is not to inform you, but to maximize engagement, to keep your eyes on the screen. It learns what triggers you. It learns that outrage travels faster than nuance. It learns that confirming your existing biases keeps you scrolling. The result is the filter bubble. The algorithm isn't a window. It's a mirror that reflects a distorted, amplified version of you back at you. This creates a fractured social reality. Two people in the same town can live in entirely different information universes. One person's feed is filled with progress and unity, the other's is a torrent of crime and conspiracy. Both believe their view is an accurate reflection of the world. The platform isn't a town square. It is a series of soundproofed rooms where the algorithm acts as a bouncer. The system is not designed for understanding, it is designed to deepen division, because division is engaging. The symmetry of a global conversation is a myth. The platform's power is to make the other side seem invisible, or to present them as extreme caricatures, the digital version of the flashed face distortion effect. It is a system of control so subtle that most of its subjects do not know they are subjects. They believe they are free. The cracks in the foundation. For a long time, we can live with these illusions. We can exist inside the Ames room. We can drive our lemons off the lot. We can scroll through our feeds, feeling informed. The hidden imbalances grind away, but the facade of symmetry holds. The system appears stable, but it can be a fragile stability. A system built on hidden imbalances is often vulnerable to shock. When the cracks appear, the collapse is not always gradual. It can be sudden. Consider our global supply chains. For decades, the world optimized for just-in-time manufacturing. It was a beautiful, symmetrical idea. Parts arrive at the factory exactly when needed, minimizing costs. It looked perfect on paper. But it created a system with no slack, no redundancy. The entire global economy became dependent on every gear turning in perfect harmony. Then came the shocks. A pandemic shuts down a region making a critical microchip. A container ship gets stuck in a canal. Suddenly, the just-in-time system becomes a just-too-late problem. Shelves go bare. Production halts. Prices rise. The disruption cascades, amplified by the very efficiency that was supposed to make the system perfect. The hidden imbalance, the world's over-reliance on a few single points of failure, was always there, lurking beneath the surface. The crisis didn't create the problem, it merely revealed it. This is the quiet danger of the systems we have built. Their perceived balance encourages a level of trust that can make us blind to their fragility. We trust that the market is a fair game, so we are blindsided when a black swan event reveals the system as a web of interconnected, fragile debts. We trust that the algorithm shows us a true picture, so we are shocked when society fractures along lines we never saw. What happens when these imbalances compound? When a supply chain disruption leads to price spikes, which are amplified by algorithmic trading, which fuels social unrest fanned by misinformation on platforms designed to promote outrage. The systems of imbalance begin to feed on each other. The visual illusion becomes an economic illusion, becomes a social illusion. The cracks link up, and the foundation of trust begins to crumble. The final day isn't a single event. It is the moment the illusion becomes unsustainable. It is the moment we look at the Ames room not from the peephole, but from the side, and see it for the crooked structure it has always been. The tragedy is that by the time we see the truth, the house may already be collapsing. Conclusion. We began with a story, the quiet myth of the balanced scale. We've seen how this idea is first born in our own minds, making us vulnerable to illusions. We've seen how that same principle of hidden imbalance shapes our economic markets, creating systems that look fair but are fundamentally tilted. And we've seen how this culminates in our digital world, where the illusion of choice can conceal algorithms that concentrate power and fracture our shared reality. From the phantom shadows in a drawing to the sorting of society, the pattern is similar, a seductive symmetry that can mask a deep unfairness. The world is not always a balanced scale. It is often a series of tilted rooms and secret levers, designed in ways that channel wealth and power, while convincing us that the game is fair. There is no simple solution. The imbalances are deep, but that does not mean we are powerless. The first step is simply to see, to reject the illusion, to stop trusting the peephole and start examining the room. To understand this is not to be cynical. It is to be awake in a world that can profit from you being asleep. The systems can make you feel that your struggles are individual failings. They are often not. They can be the predictable outcomes of an imbalanced game. Understanding this is not an excuse for inaction. It is the foundation for meaningful action. It is the beginning of empowerment. So, I leave you with a quiet question. Look around at your own life, at your job, at the things you buy, at the information you consume. Where is the beautiful lie? What is the hidden imbalance you can now see, that you couldn't see before? Start there. The day that never ended. Imagine a time before time itself. Not just before forests or oceans, but before stars, before light, before anything had a shape or a name. There was a moment, a single, perfect moment that held everything that would ever be. And in that quiet stillness, a choice was made. Reality as we know it began, not with a loud explosion, but with a subtle shift. A perfect balance was lost, and in its place, the universe we live in started to unfold. We are the results of that long-ago change. This isn't just a poetic thought, it's the story of our cosmos. It's the reason why matter exists, why we are here, and why the universe isn't just an empty stretch of dark energy. To understand it, we need to travel back to that first moment, and see how the end of perfection was the beginning of everything. This is the story of the day that never ended, the day that became our world. Welcome to the Sleepy Scientist. If this kind of calm exploration into the cosmos unwinds you, consider liking the video and subscribing to the channel. And wherever you are right now, feel free to share where you're watching or listening from. It's always nice to know where these stories are landing. A perfectly quiet universe. Before we can understand our universe, we first have to imagine one that was very different. A universe of pure, simple, and almost featureless perfection. Let's journey back, way back, before the Earth, before our Sun, to the very first sliver of a second after the Big Bang. It's a place of unimaginable heat and density. The universe is a kind of uniform, searing fog of energy, what's sometimes called a quark-gluon plasma. The familiar particles and forces of nature haven't quite separated from each other yet. In this early state, the universe was governed by a profound and elegant symmetry. You could think of it like a perfectly still, bottomless ocean of energy, where every single drop is identical to every other. Or, another way to picture it, is like a pencil balanced perfectly on its sharpest point. It's a state of absolute equilibrium. The laws of physics were unified. The forces that shape our world today, the strong force holding atoms together, the weak force that drives radioactive decay, and the electromagnetic force that gives us light, were all merged into a single interaction. For a brief period, known as the electroweak epoch, The electromagnetic and weak forces were one and the same, the electroweak force. This state of perfect balance is described by something called Noether's theorem, a beautiful idea in physics that connects every symmetry in nature to something that is conserved. For example, the fact that the laws of physics are the same today as they were yesterday is a kind of symmetry, and it leads to the conservation of energy. In this early, hypersymmetric universe, everything was perfectly balanced. For every particle of matter that appeared, an equal and opposite particle of antimatter was also born. They existed in a constant dance of creation and annihilation. A particle would pop into existence, find its antimatter twin, and they would both disappear back into a little puff of pure energy. A perfect cycle that could never build anything lasting. And yet, this is the problem with perfection. A perfectly symmetrical universe is a sterile one. If this state had continued, nothing of substance could have ever formed. No stable particles, no atoms, no stars or planets, and definitely no life. For the universe to become interesting, for it to build all the complexity we see around us, that perfection had to give way. The pencil, balanced so carefully on its point, had to fall. The universe had to choose a direction. It had to break. The moment of change. As the universe was expanding, it was also cooling down at an incredible rate. This cooling was the trigger for one of the most important events in the history of the cosmos. It was a phase transition, something as fundamental as steam turning into water, but on a cosmic scale. Physicists call it spontaneous symmetry breaking. We can think of it as the moment the universe chose the rules we live by today. This change happened only about 10 trillionths of a second after the Big Bang. As the universe cooled below a certain critical temperature, it reached a tipping point. And this is where a new character enters our story, the Higgs field. The Higgs field is everywhere, permeating all of space. In the ultra-hot, symmetrical early universe, the Higgs field itself was in a symmetric state. You can picture it like a perfectly flat, level plane. Particles could move across this plane without any resistance at all, and because of this, they were all massless. But as the universe cooled, the Higgs field changed. It found a new, lower energy state to settle into, and this new state was no longer symmetrical. A common way to visualize this is to think of the bottom of a wine bottle, with the little peak in the middle. Imagine a marble placed on that central peak. That's the symmetric, high-energy state. It's perfectly balanced, but it's not very stable. The slightest nudge, and the marble will roll down into the circular valley at the bottom. Once the marble is in the valley, it's in a more stable, lower energy state. But the symmetry is broken. It's in one specific spot, not all of them. It has chosen a location. In a similar way, as the universe cooled, the Higgs field rolled down from its zero-value peak and settled into a new, non-zero value everywhere in space. This one act had quiet but enormous consequences. The moment the Higgs field acquired this new value, it broke the perfect electroweak symmetry. Particles that interacted with this field suddenly found themselves moving through a kind of invisible drag. This interaction, this resistance, is what we experience as mass. And just like that, the universe was different. The unified electroweak force split into two distinct forces. One part stayed long-ranged and was carried by a massless particle, the photon. This became the electromagnetic force, which gives us light, electricity, and chemistry. The other part became a short-ranged force, carried by particles that became very heavy by interacting with the newly settled Higgs field, the W and Z bosons. This became the weak nuclear force, which governs radioactive decay. The weak force became weak, precisely because its carriers became heavy, confining its influence to tiny, subatomic distances. The pencil had tipped over. The universe had chosen a direction. It had acquired a new set of rules, a physics that was asymmetrical. This wasn't an event that just happened and then ended. The universe froze into this broken state. The Higgs field still has this non-zero value today. The forces are still separate. Particles still have mass. We are living inside that frozen reality. The day of perfect symmetry ended, and in its place began a new one, the day of broken symmetry, a day that has lasted for 13.8 billion years. This is the world we were born into. The echo of the beginning. This story of a quiet shift in the first moments of time is not just a compelling idea. It's a scientific theory with some really powerful evidence behind it. We can't rewind time to watch it happen, but we can see the echoes of that early universe and the results of that great symmetry breaking. The most profound piece of evidence is the cosmic microwave background, or CMB. Discovered somewhat by accident around 1965, the CMB is often called the afterglow of the Big Bang. For about 379,000 years, the universe was an opaque, hot fog. Light particles, photons, were trapped, constantly scattering off of loose electrons. But as the universe expanded and cooled, electrons and protons could finally come together to form neutral atoms. In that moment, the universe suddenly became transparent. The photons were set free, and they've been traveling across space ever since. Over 13.8 billion years, the expansion of space has stretched this ancient light into the microwave range, cooling it to just a few degrees above absolute zero. When we look at the sky with a radio telescope, we see this light coming from every direction. It's a baby picture of the universe, and its incredible uniformity is the strongest evidence we have for that hot, dense, and symmetrical early state. But the most direct confirmation of the symmetry-breaking idea came not from looking at the distant past, but from trying to recreate the energy of the early universe right here on Earth. This was the goal of the Large Hadron Collider, or LHC. By accelerating particles to nearly the speed of light and colliding them, the LHC creates tiny fireballs of energy that mimic the conditions of that electroweak epoch. For decades, the theory of electroweak symmetry breaking worked beautifully, but one piece of the puzzle was missing: physical proof of the Higgs boson itself, the particle associated with the Higgs field. Finding it would be like finding a fossil of the very thing that gave mass to the universe. Then, on July 4, 2012, scientists announced that they had discovered a new particle with the exact properties predicted for the Higgs boson. It was a quiet and monumental achievement. We had finally found the particle connected to the field that broke the symmetry, the mechanism that makes our universe the way it is. The existence of the CMB and the discovery of the Higgs boson are two pillars that support this cosmic story. One is the echo of the symmetric beginning. The other is the proof of the mechanism that broke it. They confirm that we live in the aftermath, in a universe whose fundamental laws are the frozen consequence of that long-ago fall from perfection. The story of our universe is written in these broken symmetries. From the grand separation of forces to the tiny imbalance that let matter survive, every step away from perfection was a step toward us. If you find this journey from the fundamental laws to our own existence as fascinating as I do, consider subscribing and joining us as we continue to explore the biggest questions in the cosmos. Your support helps us dive deep into these intricate stories, connecting the dots from the Big Bang to the human brain. Now, let's explore an even more personal implication of this broken universe: the very shape of life itself. The survivors of annihilation, the breaking of electroweak symmetry set the stage. It gave the universe its forces and the property of mass. But this alone wasn't enough to create the world we see. A much more subtle, and even more important, imperfection was needed. This is the mystery of why we exist at all, the puzzle of matter and antimatter. According to the laws of physics, the Big Bang should have produced matter and antimatter in perfectly equal amounts. For every particle like an electron, there is an antiparticle like a positron, identical in mass but opposite in charge. And when a particle and its antiparticle meet, they annihilate each other in a flash of energy. In the perfectly balanced early universe, this is exactly what was happening. For every billion pairs of matter and antimatter particles created from energy, a billion pairs would collide and disappear back into energy. If this symmetry had been perfect, as the universe cooled, everything would have eventually annihilated, leaving nothing behind but a cold, empty sea of photons. A universe with no substance. But that's not what we see. We live in a universe made almost entirely of matter. So, where did all the antimatter go? The quiet answer is that it didn't go anywhere. We are the leftovers. We are the rounding error in a cosmic equation. Somehow, for every billion antimatter particles, the universe created 1,000,000,001 matter particles. After the Great Annihilation was over, that 1 in a billion survivor was left behind. And from those survivors, from that tiny imbalance, everything we see was built. Every star, every galaxy, every atom in your body is a relic of this ancient asymmetry. Explaining this imbalance, known as baryon asymmetry, is one of the great challenges in physics. In 1967, the physicist Andrei Sakharov proposed that 3 conditions were needed for this to happen. One of them is that there must be a violation of a fundamental symmetry known as carbon monophosphide symmetry, charge parity symmetry. This symmetry basically says that the laws of physics should look the same if you swap a particle with its antiparticle and also view it in a mirror. For a long time, it was thought this symmetry was absolute. But in 1964, an experiment showed that the weak force, that same force born from the big symmetry break, actually violates carbon monophosphide symmetry. It treats matter and antimatter just a little bit differently. The violation is incredibly subtle, just a tiny crack in the mirror between the world of particles and antiparticles. But it seems this tiny crack was enough. It allowed for a slight preference for matter over antimatter in certain reactions. Over countless interactions in the early universe, this tiny bias added up, leading to that crucial 1 in a billion surplus. Recent experiments have continued to explore this, finding more evidence of this asymmetry in the kinds of particles that make up you and me. The first symmetry breaking gave particles mass and created the forces. But it was this second, deeper imperfection that allowed matter to survive. It ensured that the universe would not be an empty void. Our existence is a testament to a cosmic flaw, a slight deviation from perfect balance that allowed the universe to choose something over nothing. The left hand of life. These asymmetries don't just exist on cosmic scales. They seem to reach all the way down into the heart of biology, into the very molecules that make us who we are. The universe, it seems, has a preferred handedness, and this preference feels strangely connected to the broken symmetries we've been exploring. This idea is called chirality, from the Greek word for hand. Your hands are chiral. They are mirror images of each other, but you can't perfectly lay one on top of the other. Many molecules in nature are the same way. They can exist in a left-handed version and a right-handed version. In a lab, chemical reactions that make these molecules usually create a 50-50 mix of both. But life is different. Life is incredibly specific. All of the amino acids used to build proteins in every living thing on Earth are left-handed. And almost all of the sugars, like the ribose in our DNA, are right-handed. It's a universal signature of life as we know it, and it's a bit of a puzzle. Why this strange and absolute preference? A cell built from right-handed amino acids and left-handed sugars could work just fine in theory, but it would be a mirror image of life on Earth, and it couldn't interact with our world. A left-handed key won't fit a right-handed lock. The fact that all life shares the same handedness suggests the choice was made very early on. So, what tipped the scales? The answer might lie in another broken symmetry we've already met, the weak nuclear force. In 1957, a groundbreaking experiment led by the physicist Qian-Xiang Wu showed that the weak force violates a symmetry called parity. This is the idea that the universe shouldn't be able to tell the difference between something and its mirror image. Wu's experiment showed that for the weak force, this isn't true. At a subatomic level, the universe can tell the difference between left and right. In fact, the weak force seems to only interact with left-handed particles. Every neutrino ever observed, for example, has been left-handed. How could this cosmic preference influence the building blocks of life? One idea involves cosmic rays. The theory suggests that polarized radiation, influenced by the weak force's fundamental asymmetry, could have rained down on the early Earth, selectively destroying one-handed version of organic molecules slightly more than the other over millions of years. A tiny initial imbalance could have been amplified by other chemical processes, leading to the complete dominance of one-handedness we see today. If this is true, it's a quiet but staggering connection. The very shape of the molecules in your body could be a direct result of the same fundamental asymmetry that governs radioactive decay. The left-handedness of the weak force may have reached across billions of years to select the left-handedness of life. We are not just made of stardust. We are shaped by the universe's own quiet preferences. The beauty of an imperfect universe. We started this journey with a simple idea: that we're living in a single, unending day that began 13.8 billion years ago with the end of perfection. We traveled back to a time of flawless symmetry, a state that was balanced, elegant, and completely empty. We witnessed the moment it changed. A cosmic phase transition, driven by cooling, broke that perfection. The Higgs field settled into a new state, and reality as we know it froze into place. The fundamental forces separated, and particles acquired mass, creating the potential for structure. But the break wasn't clean. It left behind beautiful imperfections. A subtle flaw in the laws of physics allowed a tiny fraction of matter to survive annihilation. We are the descendants of those survivors. And the break left a deeper imprint still, a fundamental handedness, written into the laws of nature, which may have trickled down through the ages to seed life with its specific shape. From the largest scales to the smallest, our existence is a testament to the beauty of that break. We are the direct product of the universe's quiet, strange, and asymmetric history. The perfection of the beginning had to fade for the richness of today to be born. So, the next time you look up at the night sky, remember the story of that unending day. The day that began with a subtle fracture, a choice, a quiet fall from balance. It is the day we are all living in. It is the intricate, complex, and wonderfully imperfect reality that allows you to be here, now, to wonder about it all. We are not just living in the universe. We are the universe, experiencing itself as a result of its own broken symmetry. And that may be the most beautiful imperfection of all.